and through the Q&A. But I think this talk should be really interesting. It'll tell you a bit how detectors work. And then, so Evan will have a talk for an hour about the physics of particle detectors. And since we had trouble finding a speaker for today, I prepared a talk for the second hour with my colleague Ryan Linehan about dark matter detectors, so how we apply some of these detector technologies to do different types of searches. So I'm excited for today. We have Evan Niner with us here today. So before I introduce the speaker, we're going to do Brian set the stage, so we got to do it every SMP. We're all going to stand up, take a deep breath, make sure we're all here together in this room or in this Zoom room. So let's stretch our arms up, shake the body loose a bit. Made it here. Thanks for being here. Let's take 3 deep breaths, ideally in through your nose, out through your mouth. Let's take a deep breath in. Exhale. Those fingers, wiggle those toes. Deep breath in. Breath out. One more deep breath in. Let it out. All right. We have 2 talks. We have a great talk by Evan about to get started. Talk by myself and Ryan. Then we'll have a panel. We'll have 3 scientists talk to you about their path to becoming a physicist. So yeah, let's make sure we give Evan enough time. Evan Niner is a scientist at the lab. So he worked a bit on neutrino physics throughout grad school and as a postdoc on the NOVA experiment. So he did his undergrad at University of Alabama, grad school at University of Indiana, so about 4 hours away in Bloomington, Indiana. Then came to do a postdoc at Fermilab, where he has since remained working on neutrino experiments. And now he works at the test beam facility. So if you're trying to develop a new detector and you want to see how it works, they have a beamline facility where you can put your detector on the beamline and see what happens when it gets bombarded with particles. So yeah, excited for Evan to hear Evan's talk and to tell you about the physics of particle detectors. Take it away.
Good morning. It's a pleasure to be here again. I think I've been doing this for a few years now. It's great to be back. So yeah, as Nate said, I'm going to be talking about the physics of particle detectors. So how we build these detectors to do the science that we're trying to do. I'll preface by saying there's many types of detectors, and so this is kind of going to be a whirlwind tour. Some different technologies, mostly curated by the types of things we do here at Fermilab, and also my personal interests and experiences. I do include my email here. Always happy to answer questions that aren't asked during the talk today. Later, feel free to reach out and contact me with anything additional. Okay. So first, I want to start by thinking about what are we trying to do in particle physics, right? What kinds of questions are we trying to answer? And what's the purpose of these experiments, right? So we might be trying to discover new particles. This would include both things we know should be there, but we haven't seen yet, right? Recent examples might be the Higgs boson, but currently something like dark matter, dark energy. We might be also, trying to look for, things we haven't observed that we don't know are there yet. These kind of unknown particles that might be out there. We could also be doing, precision measurements, right? We have particles and properties that we know about, but we're trying to probe the framework of the standard model, search for symmetry violations, really precisely understand these properties. Something like G-2 operating here at Fermilab, looking at the precision properties of the muon. You could be probing, the origin or the early state of the universe. Is there more matter than antimatter? And many more questions along these lines. So how do we do that? Right? We basically are going through the scientific method. Right? We're going to make observations. We're going to form questions, do the research, the experiments, test these hypotheses, and then report these results. So some examples of questions that have been asked recently, right, in the field of high energy physics might be, what is the mass of the Higgs boson? are, what is the rate of electron and muon neutrinos that we observe coming through the atmosphere? Okay, so you have your question. How do you go about doing these measurements, right? So if you talk to a theorist, they can draw you some pictures. I think you'll hear about this maybe more next week in the standard model lecture. But these are these so-called Feynman diagrams, right? So a theorist would say, okay, you have two gluons that are going to fuse together. You're going to have this virtual Higgs boson. Then it's going to decay and into two photons. So easy, right? Just go look for this picture in your detector, and then you found the Higgs boson. And similarly, in the neutrino side of things, a theorist would say, well, you have a muon neutrino coming in. It's going to interact via the weak nuclear force, exchange a W boson with a neutron, and then you have a muon and a proton coming out. So go look for this muon and proton in your detector. Okay? So we can build our detectors, and there's different methods of detecting things, right? There's things that we can directly observe within our detector. For example, we can see muon and proton tracks in our detector if we construct it the right way. But then there's things that we can't see in our detectors, right? The neutrino is a neutral particle. It's not going to interact with our detector, and we're not going to see it directly. So we have to construct our experiment in a way to infer from the muon and proton that we do see, taking into account the momentum, the energy of the particles, and so on, that the neutrino must have been there indirectly to create what we're observing. So then we have to go about designing our detector to do what we want to do. So you might start by asking, your basic question, right? What's the primary goal of the experiment? What do I want my experiment to do? I want to find the Higgs boson. All right. What other measurements could I make with the same detector? Or if I modify my detector a little bit, what other science can I do, right? Because you want to do the maximum amount of science with one experiment if you can, right? It's more efficient. It attracts more collaborators, right? You might have people that are interested in similar questions, but not the same questions. So if you can all come together and build an experiment, you get more out of it by trying to think about that broader physics scope. Okay, so then you might start asking, okay, what's the event that I'm trying to see in the detector? For example, this muon and proton coming from a neutrino interaction. And how do I separate it from background events, right? Things that look like the event I'm interested in, but really aren't that. So, what's the energy of the event? How frequently does it occur? Am I seeing something that's going to have millions and millions of interactions, or am I looking at something that's only going to happen, a few times in a year or less? And how frequent is the background, right? If my background is occurring a lot more frequently than my signal, then how do I construct things to reduce that background so that I can observe the thing that I'm interested in, right? How do I separate that? And so then you start thinking about other constraints in your detector, right? How big does it have to be for the events I'm interested in? How long am I designing this experiment to run, right? Is it only going to have to last for a week? Is it going to have to live in a mine for a decade or longer? Am I building it underground? Is it in a radiation environment where it has to survive that? Am I putting it in space or in the ocean, in the ice of the South Pole? What are the rates of the data, right? I have, disk storage and computing to take into account. So what amount of data am I accumulating? How fast do I have to process it? Are these events all occurring, on top of each other? So I have to try to separate a lot of events. Do I need to build this with low radioactivity materials? Am I involving cryogenics? Does it have to resist a radiation environment? And all these sorts of questions to ultimately get down to how do I maximize the physics potential of my experiment at some, feasible cost, in some feasible scale of time. So again, I want to stress that doing this creates, a large number of people, right? You might have experiments with, thousands of people over a wide variety of expertise, right? Everyone isn't just physicists or scientists. You have a lot of, engineers, technicians, chemists, from people that have been in the field for decades, all the way down to students. There are a lot of different roles and pieces of putting these experiments together. So one of the starting points, as Nate said, I work at the test beam facility here at Fermilab. And so as you have this idea for an experiment and you start trying to put it together, often the experiment you're trying to build might require a detector technology that doesn't exist, or maybe has never been used in the application that you're trying to use it in, right? So before you construct your whole detector and spend millions of dollars doing it, you want to have some idea that it's going to work, that these components are going to do what you're designing it to do. So you might build, prototypes, small scale tests, and then, at Fermilab and other facilities around the world, we have what are called, test beams. So you have, people come for a week or two, they put their detector in a known beam with other instrumentation around it to tell them what particles are passing through their detector, where they're passing, what the energies are, and then you can quantify, the performance and efficiencies of your detector and build on that before you then build your larger detector. So we have one facility at Fermilab that does that. We also have another facility that we call an irradiation test area. So if you want to put something in a beam where it's going to see a lot of radiation, again, we can simulate that here at Fermilab and other facilities where we can, here is a picture of a set of silicon sensors that were going to be part of the inner tracker for the CMS upgrade at CERN. And we put them in a beam here at Fermilab where we simulate the amount of radiation that they're going to see over their lifetime in CMS, over the course of a day or two here, right? So you put it in the beam, and then you might take it after that to a facility like the test beam and say, okay, does the sensor still work? Did it survive? What do I need to improve upon the design before I then start making 1 million of these sensors to build my detector? So at the end result of this process, this is a snapshot of some of the detectors that we have built around the world. So here at Fermilab, this is a picture of G-2. So this is a large superconducting magnet ring that circulates muons inside of this ring with a series of detectors to measure properties of muon. Here's a picture again here at Fermilab of the NEAR detector for the NOVA experiment. This is a large liquid scintillator-based detector that's measuring properties of neutrinos. This is IceCube. This is another neutrino detector looking at neutrinos coming from extragalactic sources. So it's built into the ice at the South Pole. We'll talk about some of these detectors in a lot more detail as we go through the talk. Here's a picture of CMS. So this is doing Higgs physics at CERN, all the different layers of detector that you see here. This is the inside of ProtoDune, which is a prototype of the Dune experiment, liquid argon-based, also at CERN. This is a very large tank of water underground in Japan called Super Kamiokande that's also looking at properties of neutrinos. LIGO is a laser interferometer that was constructed to detect gravitational waves. They can come in other scales, right? This is, Crayfish is an example of an experiment that uses a network of cell phones to do cosmic ray physics. All right, there's medical applications, of course, to all these types of particle detectors. And so then you build these detectors, and what you see inside your detector isn't these nice clean diagrams. You see something like this inside CMS. So this is an example of a Higgs event in the CMS detector. This is what a neutrino event looks like inside the Super Kamiokande detector. I want you to keep these in mind. We'll come back to both of these images at the end of the talk when we've explained detector technologies and impact what they're telling us here. Then you turn all this data eventually into reports, right? You collect this data, you produce your graphs and your publications and share these results with the world. I'm going to focus on this talk really just on the experimental phase, though, right? How do we design and build these detectors? And then even more particularly, again, you can detect particles from a wide variety of sources, but I'm going to focus more specifically on, artificial sources coming from accelerators, these beams of particles, right? Here at Fermilab, we have a large complex of accelerators of different types that I think you'll hear about at various points in this lecture series, right? We're producing beams of protons, beams of muons, beams of neutrinos, other types of particles that we then have detectors. There's kind of two classical geometries you can think of when you're building a detector in an accelerator source. One is these fixed target experiments. So you have some beam coming in, it's going to hit a target of some sort, and then it produces particles coming out of that target. of different types. And so then you might have construct a series of detectors. Maybe you're tracking the particles. You might apply a magnetic field. You have a calorimeter, you're measuring the energy, you're filtering the muons, and you kind of have these layers of detectors. The other geometry you can think of is collider, right? So you have an accelerator, probably a circular accelerator. You're colliding two streams of particles together. And so the interactions there are going to radiate outward in a spherical geometry. And so you basically have to take this fixed target design and you're wrapping it around in layers coming out from this interaction point because of just the geometry of a collider experiment. So there's lots of different things that we're trying to see inside our detector, right? We might have the kind of standard model particles, right? You're going to have your collection of quarks and the particles that they build up, the protons, the neutrons. You'll have your leptons, the electron, the muon, and tau, and the associated neutrinos. You'll have your collection of standard forces, the weak nuclear force, strong nuclear force, the Higgs boson. You might have the more exotic things you're also looking for, right? Dark matter, supersymmetric particles, sterile neutrinos, magnetic monopoles, these more exotic, theoretical predictions. So we have to tell in our detector what particle we're seeing, right, and what particles we're not seeing. And so there's, a standard set of characteristics that come with the particle, right? Each particle is going to have a unique set of numbers that define them: their mass, their charge, their spin. We can use properties of conservation of energy, right, to tell us what we're seeing coming out of interaction, conservation of momentum, conservation of charge, parity, and time, or perhaps the violation of that. Particles are also going to have a characteristic lifetime. So depending on how you've constructed your detector, you could be looking at some combination of all of these properties to say, did I see an electron or a muon or a proton or something else inside my detector? So these are some of the set of tools that I'm going to dive into in a little more depth now. So starting with ionization, right? So ionization is the removal or the addition of electron to an atom. So you're going to be ionizing the medium, right? You're going to make it either positively or negatively charged. So you have some particle that's passing through a medium. It's going to be emitting energy as it does. And so some of that energy, might then knock off an electron from an atom in the medium, and then you have these ions. So you can then construct basically a detector out of this, right? You could apply an electric field, and so then these ions that you've produced from this particle passing through are going to drift, and so you have this electrical charge. By collecting that charge, that gives you an idea of the energy of the particle, right? How much energy did it put into the medium is going to correlate to the electrical charge that I'm collecting. If you build up a series of these detectors, that's going to give you a track then, right? Where did the particle pass through as it's ionizing the medium? And then you could also get timing information out of that. When did it pass through this detector, depending on how you've constructed things? And so you can have these set of sensors or, take advantage of your detector in this way. This could be done with gases, liquids, plastics, crystals, any charged particle passing through a medium could produce this ionization. Related to that, you can also collect scintillation light. This is, again, you could have, liquid, solid, gaseous materials that produce light. So yeah, as the particle's passing through this material, it's going to be emitting photons, which could then be absorbed by an atom, right? It's going to excite the electron, and then when it de-excites, it's going to emit light. It's going to emit light of a very specific wavelength that's characteristic of that material. And so you can have, lots of different, scintillating materials, right? They could be organic or inorganic. Depending on the material you select, as I said, it's going to have different properties, right? What's the wavelength of light that it's emitting? What's the time scale on which it's exciting and de-exciting and emitting that light? And then, of course, we have to then collect that light, convert it to some kind of electrical signal. So this can be done with a variety of photomultiplier tubes, photodiodes, photomultipliers, to collect and count these photons. Similarly to ionization, this can give us information on the particle energy, right? How much light am I collecting? The tracking, when did it produce the, when did it pass through the detector and produce this light, and also the timing. So one of the types of detector we can use for collecting light is a photomultiplier tube, right? So we have light coming in through a window. It's going to hit a photocathode and then produce photoelectrons via the photoelectric effect. I construct my tube with this series of diodes, these metal planes at increasing voltage. So as the photoelectrons are passing through, they're going to be accelerated from one stage of my photomultiplier tube to the next, and that's going to produce, a cascading effect where I get an amplification of the photoelectrons at the output to the input. Gains are typically around 10 to the 6th. So for a small amount of light coming in, I get a larger electric signal. It stands out from the background, dark currents in my photomultiplier tube. These come in a variety of different temperatures. They might operate in different temperature regimes at different voltages. They come in large, different sizes, right? You might want a very large, 20-inch photomultiplier tube. In some applications, you might have smaller ones in others, and other operating characteristics that we'll get into in a second. So one of the important things in a photomultiplier tube is the quantum efficiency, right? So I'm showing you here a plot of wavelength of the light coming in, the wavelength of the photon that's going to hit my tube. And then the quantum efficiency is how efficient is that photocathode window at converting the light into photoelectrons. Ideally, you would have 100%, but in practice, it's going to be less than that. And you see that for different materials that I've selected, they have different efficiencies for different wavelengths. So if I know that the medium that I'm in, the frequency, the wavelength of that light is in the couple hundred nanometer range, I'm going to select a different material than if it's out in the infrared. So that determines the design of your detector. Sometimes it might lead you to put something called a wavelength shifter into your detector, right? So I have my scintillating material that's producing light that's not at a wavelength that's efficient for my detector. So then I've doped it with some other additive to absorb that light and then re-emit it at a different wavelength that is more favorable for the detector that I'm using. You can also have an avalanche photodiode. So this is typically a silicon detector. I've constructed this diode out of layers of silicon that I've doped in different ways to have an enhancement of electrons in some layers, a depletion of electrons, these holes in other layers, and I've applied a voltage such that, again, when you have a photon coming in to this absorption layer, again, it's going to knock out an electron, be accelerated through a multiplication stage, this increasing voltage, where you get some increased amount of electrical signal coming out. Gains are typically lower than phototubes. It can be very sensitive to these operating voltages. You might be lowering the temperatures here to reduce the dark currents. These are typically much smaller in coverage size. So you think of these photodiodes as being, much more handheld than a photomultiplier tube. I can take this one step further into something called a photomultiplier. So these are typically a series of microcells, right? So thousands of very small microscopic cells. Each of these cells is in essence a silicon photodiode, but I'm operating it in this over voltage regime, something called Geiger mode, so that I have one photon coming in, and it's going to produce a very large cascade of electrons coming out, maybe gains on the order of 10 to the 6th. And so if I had multiple photons coming into the same cell, I couldn't tell the difference. I'm going to get the same burst of electricity coming out. But because I may be operating in a very low light regime, and I have these microcells so that I'm not expecting more than one photon in one cell at a time, it lets you get these very clean images where you can really count the number of photons that are coming out if you've calibrated it right. So here's the plot showing you the dark current, right? 0 photoelectrons, and then here's 1, 2, 3, 4, 5, and so you get this crisp, distinct image of how much light did I see in my device. I want to focus in a little bit now on the NOVA detector. This is an experiment that I worked on, and using it as an example for some of these technology choices. So NOVA is a very large detector. It's 14,000 tons, the far detector. So it's made out of very long strips of PVC plastic cells. Each of these cells is about 15 meters in length. Inside of these cells is a liquid scintillator, so it's mineral oil and some other additives. So when I have a charged particle passing through one of these cells, it's going to produce scintillation light. That light is collected in an optical fiber that runs up and down the length of the cell, and then is connected to a photodiode, so that you see the amount of light that was deposited. And then because you have the light collected in these individual cells, it's basically like a honeycomb grid. You also get the tracking information about where did the particle go. And so for NOVA, this is again a plot of the wavelength of the light, and then the quantum efficiency of the detector technology. And so the light that I'm producing coming out of the liquid scintillator, I'm showing here in this black curve. So it's peaked at around 430 nanometers. Right in kind of the blue light regime is what's coming out of the liquid scintillator. That gets absorbed by this optical fiber, and then the light that's passing through the optical fiber is shifted. So it's somewhere between 500 and 600 nanometers, so kind of in the green spectrum of light. And you see that the intensity of the light and the wavelength depends on the length it's traveling in the fiber, right? If I'm right at the top of the cell and it doesn't have to travel very far in the fiber, I'm getting more intense light. And it's also, closer to the 500 nanometer regime. That wavelength is shifting as it's traveling further down the cell, and I'm also losing light, right? It's attenuating as it's traveling through. And so if I had a photomultiplier tube that was at the end of these cells, it has a much lower quantum efficiency, particularly at the wavelengths that I'm interested in here, than selecting an avalanche photodiode. So that can make a large difference in this type of detector, right? Between did I see the particle or not? Is it just missing from this cell because I wasn't sensitive enough to the light that was being produced? And so that's why the NOVA experiment selected these avalanche photodiodes, again, for its particular application. Doesn't mean that the photodiode is the right choice for any detector or application, just for this one. So again, I can take these techniques that I've now talked about, the ionization and the scintillation, and I can do tracking with this, right? So I can track my particles into discrete steps. So this is a picture, again, of the very inner layers of CMS, which has millions of these silicon photodiodes to separate the tracks coming out of a collision of proton beams at CERN, where you're getting quite a large number of tracks. Right. What I want in a detector is the best tracking resolution that's required to make the physics measurement. Right. I don't want a lot of dead material. That's the boundaries of these detectors, the space between them, because that can degrade my energy resolution. I want to see where the particle's going, but of course, the more channels in my detector I produce, the higher the cost, and also the more data that I have to process, right? The more disk it takes up, the more processing time. And so I want to have everything I need, but not necessarily more than that. So then another example, right, is IceCube. So again, it's taking advantage of just the volume of ice at the South Pole. So it's using the ice as the detector medium, and it's looking at neutrinos coming from extragalactic sources. So they pass through the ice. They produce quite a large amount of light. They're extremely energetic. And so I basically just drilled into the ice, and I've strung photomultiplier tubes like Christmas lights into the ice. Here the spacing is, I think it's on the order of 17 meters. That's right, between these lights, right? So very, very large spacing, because I don't need the granularity that I do in CMS, to see this extragalactic neutrino source. Another thing that we can use in identifying particles is magnetic fields. So of course, this only applies to the charged particles that we're producing. But as a charged particle passes through a magnetic field, it's going to curve, right? And of course, it's going to curve in a different direction if it's positively charged or negatively charged. So that lets me distinguish between a particle and its antiparticle. And then by the curvature, that lets me measure its momentum. So I can do the momentum reconstruction. I can do this distinction of particles by how it's curving. But again, it's not going to work for my neutral particles. A neutron's going to pass through. Photons, neutrinos will go through undeflected. Another important part of a detector is calorimetry, right? So that's measuring the energy of the particle inside the detector. Of course, to fully characterize the energy, you have to be able to stop it, right? If a particle passes through my detector and hasn't stopped, it's carrying some energy with it that's unknown to me, and so that degrades the resolution of the experiment. I don't know exactly what the energy of the particle was. Right? There's different types of calorimeters. I can use different materials, and of course, the particles have different properties, right? And so you might construct your detector in layers, right? I don't want to stop everything all at once because then everything just looks like a blob. I can't see the track or maybe tell the difference between the particles. So I might have a tracking chamber that things are going to pass through. Of course, the photon and the neutron being neutral might not leave anything here. And then I have an electromagnetic calorimeter. I'm going to stop my photons and electrons, be able to measure that energy. Then I've built up a hadronic calorimeter, take advantage of the strong nuclear force, stop these other hadrons, and then range out the muons. So showers, evolve differently depending on the particle type, right? So in a hadronic shower, I have a pion, a proton coming in. It's predominantly going to interact via the strong nuclear force. That's going to have a characteristic interaction length dependent on the particle and the material. It's going to, as it's passing through, it's going to be depositing energy, scattering, knocking off other pions. There might be an electromagnetic component as well. It's going to produce some photons, and slowly deposit all of its energy. For electrons and photons, these are going to produce electromagnetic showers, right? They're primarily interacting, depositing energy via bremsstrahlung radiation. So I have an electron passing through the detector. It's going to scatter, produce a photon. That photon's then going to pair produce after some distance where it's producing an electron and a positron, and this shower is going to continue to cascade and evolve. If you notice, though, there's a difference between the very beginning of an electron shower, where I have this electron depositing energy immediately, and a photon, which is going to pass through some distance undetected. And then when it starts showering, I have two electrons worth of energy in this first layer, or really an electron and a positron, versus one layer. So I've constructed my detector in the right way. I can tell that difference between one electron's energy and two, and distinguish an electron from a photon. You also have this gap, right? This distance the photon's going to travel before it converts into this electron-positron pair, and I can use that distance maybe to distinguish the particles. I can construct my calorimeter in different ways. So I can have what's called a sampling calorimeter, where I might have layers of material that I'm using to collect the energy of the particle, and then maybe layers of interacting material, maybe something like steel or other things that are causing the particle to shower. And so I'm sampling the energy along the way. I'm also sampling the shape of the particle along the way. I could also have a homogeneous calorimeter, right? I just have a block of material maybe connected to a photomultiplier tube. Electron comes in, deposits all of its energy, and I see it. So maybe I've captured 100% of the energy that way, but I have no sense of the shape, right? How did that shower evolve, and maybe how did it differ from the photon shower, but I've collected the energy. Another technique that we can use is called a Cherenkov radiation. So as you're likely familiar, right, is, you know, a plane or something equivalent traveling faster than the speed of sound produces a shock wave, right? It's traveling faster than the speed of sound in the air, produces this buildup of the shock wave behind it, can break the sound barrier. You can have the same that's true for light as well, right? A particle can travel faster than the speed of light for a particular material. So it's not traveling faster than the universal speed of light, but in that material, different materials have different speeds. I can then travel faster than the speed of light and have this light cone, this Cherenkov radiation that's being built up behind it. It's going to have a characteristic angle. So this depends on different properties, right? Each material is going to have an index of refraction for the medium. You know, of course, I have the speed of light in a vacuum, and then the velocity of the particle. So if I'm traveling fast enough, the particle, I can cross this threshold where I start producing Cherenkov radiation. And, you know, again, depending on the speed and the material, I'm going to have this angle of this cone of light. Here you're seeing inside a nuclear reactor, you know, this blue glow that you're seeing in the water is Cherenkov radiation, you know, coming from the neutrons. So I can do this to do particle identification, right? The angle depends on the velocity and the mass and the material. So I can get direction information from this cone. Where is it pointing? Timing information, particle identification. I'm collecting the light, so that gives me the energy information as well. So here's a plot of momentum of particles. This is from the ALICE detector, and then this is measuring the angle of that Cherenkov radiation. So then I see that for pions, kaons, and protons, you know, there's this separation, right? For a given momenta, I'm seeing different angles inside my detector, so I can distinguish the particle that way. Of course, eventually you get to a momentum where I'm energetic enough where everything breaks down and is indistinguishable from itself. So it only is working in certain regimes. I can apply this property, you know, quite frequently in neutrino experiments. So this is something called a water Cherenkov detector. So I'm identifying the particle by the topology of the ring. So I have a neutrino passing through the water. It interacts with the water, you know, produces its charged particle, the muon or the electron coming out of that interaction. You know, as the muon or the electron travels through the water, it's going to produce this cone of light, the Cherenkov radiation, and then I have a series of photomultiplier tubes to collect that light. And so here's a couple of images from the Super Kamiokande experiment. So on the top here, this is a simulated muon neutrino interaction, where you see there's this very crisp ring. And in the bottom here is a simulated electron neutrino interaction. You notice that this electron ring is, you know, much blurrier. There's a fuzzier shape to it than the muon ring. And it's because of the mass difference between the particles, right? The muon is about 200 times more massive than the electron. And so it's traveling in a much straighter path through the water. The electron's going to get knocked around, it's going to scatter, it's going to change its path. And so that produces a fuzzing, this blurring of the cone of light from the Cherenkov radiation. And so the Super Kamiokande experiment uses this, you know, quite successfully to distinguish, did I see a muon neutrino or an electron neutrino in my detector? I'm also getting timing information, direction information, where does this cone point back to? And I've collected the energy of the particle. So putting these techniques together in another way, right, this is a liquid argon time projection chamber. So I have very large volume of liquid argon. I have my particle that's passing through. Yeah. So I have a charged particle that's passing through this liquid argon. It's going to do two things. It's going to produce ionization. It's going to ionize the liquid argon. And I've applied an electric field here. Right, I have a cathode plane and a series of anode wire planes. And so these electrons that I've ionized are going to drift to the anode plane, and they're going to deposit their energy in these wires. And so because I've constructed these wires in different directions, I get in, 2 dimensions this track profile, right, of where did the charged particle go, and I've collected its energy. What's also happened here is I'm producing scintillation light. So in addition to the ionization, the particle has produced scintillation light in the liquid argon. So I can also have, photomultiplier tubes or photodiodes, and I collect that light. And that's why it's called a time projection chamber. So I'm going to see the flash of light first, and then the ions are going to drift and be collected. And by knowing the time difference, the time it takes for the drift, I can then project that third dimension of where inside my detector did the interaction take place. So argon has a lot of nice properties, right? It's a noble element, so it has little re-interaction with the electrons that I produced via ionization. It's less likely to reabsorb them. It's nice that I get the scintillation and the ionization light. It's a relatively inexpensive material, so I can build a lot of liquid argon or gaseous argon at a reasonable cost. It's also a nice density too, right? I want a more massive detector, and so picking something like that is cheap, but also will encourage interactions is advantageous. And again, I'm getting this tracking, calorimetry, and particle ID all in one. So here's one application here at Fermilab. This is a recently running experiment called MicroBoon. This was a liquid argon time projection chamber that was looking for neutrinos. So in this case, the beam is coming in here from the right side. For a neutrino, of course, the neutrino is not leaving a track. And then you see in this image, there's this interaction point that must have come from the neutrino. And then you have these tracks coming out. You also see likely a photon here, right? There's a gap from the interaction point, and then some more electromagnetic showers that are taking place. These are very crisp, high-resolution images, right? I have very fine wires, seeing exactly where the particle went. I'm collecting the energy. In the background here, you're seeing cosmic rays coming from the atmosphere, these background events that I'm trying to separate from the neutrino interactions. So taking the concepts we've talked about and now thinking about applying them to a collider experiment, right? I'm having my accelerator that's steering the particles, these proton beams to collide. So the particles are going to radiate outward from this interaction point. So I want to build my detector in rings. I'm going to have a very high multiplicity of interactions. So I need a granular detector with very fast technologies and radiation hard components, right? I'm talking about hundreds of interactions in a very small space, in hundreds of picoseconds. And so I need, fine timing, small detectors. I'm going to apply multiple detector technologies so I can efficiently collect and identify all the different particles coming out here. So this is what the CMS detector looks like. It's built in layers. So at the very inner point here is the beam pipe, and at the center, this would be where they've designed the experiment to steer the beams to collide. And then coming out of that first is the silicon tracking layer, where again, I've got 124 million channels in my inner pixel layers. And then wrapped around that is the electromagnetic calorimeter to measure the energy for these electrons and photons. Then wrapped around that is the hadronic calorimeter. Then I have all of this in a solenoid, so there's a magnetic field that's been applied to this. And then there's the muon trackers wrapped around the outside here. So different particles are going to behave differently in this detector, right? If I have a photon here in blue at the top, it's going to pass through the tracking layers, undetected. It's not going to be depositing energy. And then in the electromagnetic calorimeter, tried to induce this interaction in the photon, and I see the energy deposited from it. An electron is going to deposit energy in the tracking layers, and then also be stopped in the electromagnetic calorimeter. We see a muon traveling through all of these layers depositing energy. A charged hadron, something like a pion, is going to be reached out in the hadronic calorimeter, and so on. So coming back to this image, right, of, I have my collision point here inside the CMS detector. We see in orange all of these tracks that are coming out through the silicon tracking layers. These two interactions here in green, right? So this is energy, a large amount of energy that's been deposited in the electromagnetic calorimeter layer of the detector, and you see that it doesn't correspond to a track in the inner tracking layers, and so that identifies that I'm seeing two photons with energy deposited, and then reconstructing, the angle of these photons, the energy, and so on. That gives me information about the Higgs boson that might have led to this decay. Can also then think about this in the context of neutrino experiments, right? So in neutrino experiments, the interactions are very rare, as you'll hear about, I think, in a later lecture, right? Neutrinos only interact via the weak nuclear force. They're much rarer, and so I want to build a very large detector, typically with as much target mass as possible, to increase the probability that the neutrinos interact. If I'm an accelerator experiment, I want to have the most intense source of neutrinos as possible. I want to have a very high-powered beam, and I'm going to run the experiment for decades, typically, right? I'm going to run for a very long time to accumulate interactions. I want to try to minimize the background sources, have very good energy resolution and particle identification, because if I'm not seeing very many events that I'm interested in, I need to do a very good job of separating them from the events that I'm not interested in. So again, one example of this that's being constructed here at Fermilab is the DUNE experiment. So this will be a beam of particles coming from the accelerator here at Fermilab that will then produce a stream of neutrinos that'll travel about 800 miles through the Earth to an underground facility in South Dakota, where we're building a very large, time projection chambers, both liquid and gaseous argon. We're talking, on the order of 10 kilotons, per detector in this far site. So this is a picture of the inside of one of the prototypes for DUNE. Again, it was in a test beam at CERN to understand its properties before DUNE is built. So this volume here is filled with liquid argon, and you're seeing kind of in gold on this side is the anode plane. What you're seeing is this wire mesh that's collecting the ionization. And I think you can also see, if you look behind it, there's these rows here of these white planes, and so those are the scintillation light collectors to collect that light component from the interaction. So with that, I'm going to wrap up. I think I've given you a whirlwind tour. I hope I've impressed that there's very many technologies out there for identifying particles, a lot more than what I've covered today. Really, the name of the game, right, is optimizing your detector design to satisfy a set of physics goals. There's no one way to build an experiment. There's no one technology that's always the correct choice. We have a lot of tools in our bag here that we can put together in different ways for the physics questions that we're trying to answer. And I hope I've also stressed that as much effort goes into designing and building these experiments as collecting and analyzing the data at the end. It really takes a large number of people from a wide variety of skill sets to put together these experiments. With that, I'm happy to take questions.
Thank the speaker. All right, questions. Yes. Yeah. So let me pass you the mic, or you can.
Oh, so I know you talked about how you use liquid argon in these experiments. Would there be any other noble gases that would be better than argon, but are maybe too expensive or are not
I wouldn't necessarily
enough?
say better. There's different gases you might use for different regions. There are xenon examples, right? There are xenon time projection chambers, and I think that's going to be talked about in the next talk, actually. So that's a good segue. Yet you would make different choices for different reasons, right? Some of it depends on the type of physics that you're trying to do. That xenon might be a better choice. There are also cost considerations and so on. If I want a 40,000-ton detector, I'm not getting that with xenon. But there's other reasons why you might make different choices.
When talking about the different environments that you can build detectors in, you mentioned space as one. Have we actually put a particle detector in space?
There are a lot of varieties, right? There's a number of, satellite experiments, right? You put different payloads in space, collecting particles and so on. Yeah, there's a lot balloon experiments. You might fly payloads at the South Pole or other places. Yes.
There's a lot of, well, you can, if you're trying to build something and put on space, there's space on the ISS to put instruments. Yeah, people build balloons. You have to get a lot of funding to build your own satellite, but they're all are like, I work on a CubeSat experiment for building a small experiment, and you can get a rideshare opportunity to get it onto the ISS, and they basically just push it off the ISS. So there are detectors in space, but it is hard. There's more challenges compared to on the surface because there's a lot of charged particles, a lot of higher background rates than compared to like underground. Like Dune's going to be underground to like reduce the background rates, but when you're in space, you don't have shielding. You just get hit by protons and charged particles that deposit a lot of energy. So it's different challenges, but there are a lot of charged particles in space. I'll talk a little bit about that in the next. Other questions? Anything on Zoom? Anything else? Yes.
What is the reasoning behind having an experiment at the South Pole? Like, what is unique about the ice that you would want to build a big experiment there?
So thinking about IceCube, I mean, a large part of it comes to cost, right? Again, you want a detector that's gonna fully capture the energy of the particles that you're seeing. And when you're talking about an extragalactic, neutrino source and the energies of these neutrinos, you need something very, very large, right? IceCube is, a cubic kilometer of ice that's been instrumented. And so trying to build that, out of a classical, like a water tank or something just isn't feasible. So taking advantage of, the construction of the Earth, that, that there is this ice that you can just instrument is useful. Going there, right, you have a lot of ice at the South Pole that also is optically, very pure, right? So you can get the light traveling through the ice. It's not going to be absorbed. You can instrument it. So I think that's why ultimately, that technology was selected for that choice. Again, for accelerator experiments, right, you're talking about energies on very different scales and orders of magnitude. So you can build a much more manageable detector to, range out a neutrino, from nova, for example, versus these other sources.
So on IceCube again, how do you I would assume that the ice would have to be very specifically, like, I don't want to say pure, but you can't just use any ice for it, I would assume. So how do the scientists there, like, keep out contaminants from the ice if it's just at a place in?
So ultimately, they can't change the ice in that way, but I imagine, IceCube has been operating for a number of years, so it's not at the surface of the ice. It's drilled, down, this cubic kilometer of ice is, buried. So I believe you would have taken sample measurements, right? You would have drilled and pulled the ice out of different depths. You would have studied it. You would have probably sampled your entire region that you're looking for at the detector before you select the point. So you would have measured that uniformity. Is this good ice? Is this going to work in that way? Right. Ultimately, IceCube is working off of the same Cherenkov radiation technology as the water Cherenkov detectors like Super Kamiokande, right? What you're producing is that when the neutrino cosmic ray passes through, interacts with the ice, it's going to produce this Cherenkov radiation light that you're then collecting in your photomultiplier tubes.
Do one more.
Could you just explain again how come like the image that the Cherenkov light of like an electron is like more blurry than like a neutrino?
Yeah, so the electron is going to scatter more in the water, right? It's a much lighter particle. interacting primarily via Bremsstrahlung radiation, it's going to have more kinks in its path. It's going to be scattering, and so because its path is changing, you can think of that cone of light that's trailing it is also wiggling. It's changing its direction, and so it's going to produce this fuzziness in the image that you're seeing. Whereas if a muon's just traveling straight through, it's producing a cone that's much more stable. And so you're just going to measure light in a ring that's going to kind of stay static, right? So that's why you're getting this difference.
So a brief aside on detection. So Evan was just talking about detectors, but I thought I'd just kick it back to the basics. How do we see things? Which is, I mean, when I was putting these slides together, it's like kind of meta. I'm using my eyes, I'm looking at the screen, but there's all this stuff happening behind the scenes that we take for granted. Maybe you already learned this in biology. A biologist or a neuroscientist knows a lot more about this than I do. I know more about cameras and telescopes. But the analogy between our eyes and the camera, so we have, there's different layers. There's a cornea that kind of starts to do some initial focusing. Our light goes through the pupil. Our iris, expand and contract to let more or less light in. So your pupil is like your aperture in camera technology, or how big the hole is that's letting the light in. And then, there's another lens here behind the pupil, but the light gets focused on the retina. So the analogy for the retina is, in a camera, you have some sort of detector. It's usually like a solid state detector, like a semiconductor. You might have heard the term CCD, which stands for charged coupled device, or CMOS. I need to just find that acronym, but it's basically a type of detector technology made of semiconductors, usually silicon, that converts the light into an electrical signal and sends it to your data storage device. So in this case, it sends electrical signals to the brain, and the camera it sends to an SD card or whatever storage device you have. So usually most of the stuff that we see comes from light and the electromagnetic spectrum. So it's interesting, radio waves really is a form of light. The visible range of light, what we see in our everyday, is only so much of the electromagnetic spectrum. There's a lot that we can't see with our own eyes. So you have to come up with detector technologies to be able to detect, so for low frequency, let's see. I always mess this. For lower frequencies, yes, that's longer wavelengths. They're inversely proportional. You kind of get into radio, so RF, so AM radio is kind of in this band, and FM radio. I more work, so Dylan does a lot of RF stuff. I would botch it if I try to talk too much about it. I work more in high energy astrophysics, so X-rays and gamma rays. So I'll talk a little bit about that and different photon processes. So yeah, we can always see within the visible range, but how can we detect photons outside of the visible range? You come up with some sort of detectors. Usually they exploit photon processes. So light interacts in a range of ways. The three main ways are, so photoelectric absorption. In this case, this is kind of maybe more familiar. So you have some atom. This is the photoelectric effect that Einstein discovered. You have some atom. There's electrons orbiting the atom with some characteristic energies. If the photon has enough energy, it can kick out the electron. The electron has some kinetic energy coming out of it. Sometimes that ionizes other electrons in this material. But basically, there's some energy associated with kicking the electron out, and the remainder of energy gets given to this electron, which then deposits other energy in your detector. You're able to reconstruct the energy of the photon from this electron that comes out. So that's basically what's happening in, that's more familiar in our, well, I forgot to say rods and cones. I wanted to say rods and cones. That's what serves as basically the detector for our eyes. So that's just the light's absorbed. But there's also, as you go to higher energies, other processes, become more dominant. So I'll show you a plot, but for Compton scattering is essentially for X-ray photons is more dominant. So in this case, the electron scatters off. So it kicks off an electron. So it scatters with the electron, but the photon isn't absorbed. It keeps moving through the material. This was found by a guy named Compton. He has this process named after him because he derived the theory for Compton scattering. Pair production dominates at higher energies. This is when you go above an MeV usually. So energy has to be conserved in all these things. So So usually for a gamma ray photon, or it's usually above an MeV, it produces an electron and a positron in a pair. So an electron its rest mass energy is 511 keV, and same for the positron. So the photon has to have above like 1 point, whatever MeV for that process to occur. So these are the three main photon processes. They're energy dependent. So this pink curve is for absorption. So you see at low energies, most of the light is just going to be absorbed. But then if you want to detect photons in this energy range, around an MeV, the dominant process is that constant scattering. So you have to get creative in, coming up with a detector to detect, the scattering of photons as they go through the detector, and then being able to reconstruct, where the photon came from. That was actually the first research project, was like designing a Compton telescope, which flew on a balloon, and now they're building a satellite to detect, photons in this energy range, which is interesting for a wide range of reasons. They call this the MeV gap. Like, a lot of astronomy has looked at visible light, but if you want to detect photons in this energy range, there haven't been a lot of observations because it's hard. You don't absorb the photon. You have to, get all the scattered photons and reconstruct where it came from, and yada, yada, yada. Pair production, there's the big satellite is called Fermilab, or Fermi Large Area Telescope, that exploits pair production to look at very high energy gamma rays. So anyways, this plot might come up. So it's basically photon energy is a function of what I would call basically cross section, or it tells you the probability of an interaction occurring. So this just tells you where different processes dominate. I'm going on and on about this because I think it's somewhat relatable to Evan's talk, and also I think it sets up the stage for why it's hard to detect dark matter. Photon processes are probabilistic. Like, there's, this just tells you the probability of this interaction occurring. But when light goes through, it has some chance of interacting or not. So usually the way they set up this problem in like your homework textbook is you have some beam of photons coming in, and then this curve tells you the probability of a photon getting scattered out of the beam. Or say you shot 100 photons in, this would tell you how many photons would come out of the other side of the material. So this mu depends on the density of the material, the atomic structure of the material, but also, ultimately the thickness. So anyways, TMI, but if you multiply this by your density, so grams per centimeter cubed, you get something that's 1 over distance, and that kind of tells you like the characteristic length scale for a photon interacting in your detector. Units are very useful for figuring out what things mean. So that's like the mean free path of the characteristic, length of interaction. So I'm going on and on and on. Anyways, the only other thing I want to say is, so unlike photons, charged particles deposit energy as they move through a material. So I work with CCDs, which are basically like the chip in your camera, but charged particles, they deposit energy on their track. So as they're moving, they create ionization, and we hook up a battery, an anode and a cathode, as they're talking about in the chat. And so when those electrons get ionized, they basically drift under the electric field, and we can collect them through some various things I can talk about afterwards if you want. But you get these tracks. This is what a muon looks like. The electron is more wiggly because it's a lighter particle. And X-rays or photons, they interact in one position, so they look like little circular blobs. But this is what charged particles look like in my detector. This is, I believe, a bubble chamber image. This is pair production. So this is interesting because you can't see the gamma ray photon, right? But you can infer that it was there based off of the other, events. So photons aren't charged; they don't leave tracks. But when it does pair produce, it produces two charged particles. And so this is an electron and a positron. In this case, they have a magnetic field, which, I don't know if you've learned the Lorentz force, but basically moving charge in a magnetic field will get deflected according to the sign of its charge. So because the electron and positron are oppositely charged, they'll move in different directions in this material. And if they're really high energy, their tracks won't be as more or less curvy depending on how fast they're moving in the material. And so anyways, charged particles, usually there's a lot of theory that defines so how much energy a charged particle deposits in a material as a function of its momentum or velocity in these weird units. Usually you learn this This is the beta block region of this curve. This Hans beta kind of drive the theory, and Felix block. I just think it's funny because when I was in grad school, I thought it was beta block, like the Greek letter beta, and like block, like stopping, but it's really two people's names. So anyways, the beta block theory, kind of tells you how much energy a charged particle will deposit, and it's named after two physicists. It's not beta block. Anyways, okay, what about dark matter? So I've told you, like, photons, charged particles, how they interact in our detector. Dark matter is one of the big questions in particle physics, astroparticle physics. I'll explain a bit. Particle physics aims to figure out, what's the world made out of? What are the fundamental building blocks of the universe and everything around us? What are the forces that act between them? So conventionally, you would see these types of searches going on and this is the LHC. So you have a big particle collider, detectors around the ring. We'll have a talk about the LHC next week. Through particle physics, we've learned a lot about the universe and what makes up the universe. So this is the standard model. You're going to learn all about it next week. I think it's pretty amazing. So up, down quarks makes up protons and neutrons, electrons. This is basically everyone we know and love, everything, the trees, the water. There's further classification between bosons. So bosons are spin, integer number spin. Fermions are half number spin. So, your electrons are fermions. Yeah, so there's like classification, but basically the standard model of particle physics has been extremely successful in describing the interactions that we see at the LHC. The standard model, one of the predictions of the standard model was the Higgs boson was finally detected at the LHC. So just a brief aside, at Fermilab, the top and bottom quark were discovered. The bottom quark was discovered in 1978. Leon Lederman developed this, led this experiment that discovered the bottom quark, then became the director of the lab from 79 to 89. I chose this picture because it's literally like right out there is where this picture was taken. You can see, you can actually probably walk out there. There's a little statue. So this was, great man, did a lot of great work, led the lab, and helped discover the bottom and the top quark. The top quark was eventually discovered later in 1995. Can anyone have any idea why was the bottom quark found before the top quark? Any ideas? Yeah, what do you think? Yes. In the room, people on Zoom, lower mass. So in general, with these particle colliders, you try and create higher and higher energy beams so you can access and create higher and higher mass particles. So I think, at this time, it was in 78, they made some improvements to the beam to get to higher energies, better detectors, and they were able to find the top quark. And yes, so that is particle physics as we know. But so a little bit about particle astrophysics, which is, kind of the field that I'm in. Basically, you can use astrophysical measurements to tell us stuff about the universe. The particles we observe, and colliders also exist in space. And in fact, some of the, our colliders don't have nothing on like a supernova, like the stuff that's created in these, like the energy scales of the accelerators. So what is this? This is like, it could be what they call, a PeV, or what do they call it? Basically, it accelerates particles, they think up to PeV energy. So the LHC is at like 13 TeV. The idea is like some of these, there's so much mass and gas in these systems that you can accelerate particles up to really high energies you can't get in accelerators. So this is an X-ray binary system. I think this is, so usually it's a compact object like a neutron star or a black hole, and it has a companion star. And it creates gas from the companion star, and it kind of swirls around, heats up, creates this plasma, and then creates like, there's still questions about how it actually accelerates the particles, but usually it's like creates a magnetic field. The swirling charge creates a magnetic field that then creates a beam of particles shooting out. This is called SS433. I did a little X-ray observations of it when I was in grad school. CMB is also a part of particle astrophysics. We will have a talk about cosmology in a couple of weeks, but I do have a couple slides about it as it pertains to dark matter, but I'm by no means an expert. So if you can ask questions, I might not know the answer. Okay, so let's talk about dark matter. Why do we think it's there? Or what is the evidence for dark matter? The first evidence came in 1933 by this guy, Fritz Zwicky. I think this will also pop up in the cosmology slides. But he looked at the virial theorem. I don't need to get into that. But basically, so if you look at, the virial theorem told him basically how much gravitational potential energy this cluster, this coma cluster had. And then he looked at, the gravitational energy, and he looked at how fast everything was moving, and found that, the rotational velocity, or the speed at which things were moving, was too fast to be solely supported by, the visible matter that he saw, the visible matter that was exerting a gravitational pull on the stuff that was rotating around it. So this was in 1933. I mean, it's pretty clever to, apply this physics. So that was the first evidence. He called it Dunkel Materie. I don't know, he's German, or I think Polish, but I forget exactly. I should have looked that up. But so that was the first. So maybe there's this dark matter out there that's, exerts a gravitational force but doesn't interact with light. More evidence for this came around the 70s through observations of galaxies and how they rotate. So this is a galactic rotation curve. So if you look at the luminous mass in the galaxy and how it rotates around, you would expect a certain velocity distribution just from, so this is mv squared over r. So this is like, if you're, moving your arm in a circle or something, or if you have a ball on a string, it's basically the acceleration that it feels. So you have to have, in order to keep something in a gravitational orbit, the gravitational energy has to be able to exert enough force to keep it in the orbit. If it's moving too fast, it won't be held in the orbit. But so if you looked at the luminous matter, you would expect this distribution of velocity as you move further and further out. But what they found, so Vera Rubin did a lot of these studies in the 1970s, was that basically the stuff in the galaxies is moving faster as you move further and further out than what you would expect just from the luminous stuff that you could see. And so this was more evidence that maybe there's some stuff in these galaxies that we can't see that's exerting a gravitational force, but it's non-luminous, so it doesn't produce light, doesn't interact with light. And this is kind of what that looks like in a video. So this is like what you would see for, traditional Keplerian. You can kind of see that, as you move further out, stuff is moving faster on the right than it is on the left. So it's kind of one of the big evidence. So basically, there's a lot of evidence through, basically, if you assume our theory of gravity is correct, which there have been alternate theories of gravity suggested to reconcile these discrepancies, but they haven't really stood the test of time. If you assume our theory of gravity is correct, we need a new particle to explain these observations. There's also a lot of evidence in cosmology. So we'll have a full talk on cosmology. So I won't get into the nitty-gritty details, but cosmology studies, well, basically the birth of the universe and the evolution of the universe on large timescales. So going from the Big Bang to period of inflation, and then as things expanded out. And so a lot of the evidence for dark matter comes from cosmology, because the idea is that dark matter has been around since the beginning of time, even though we don't interact with it, but it did play a fundamental role in how galaxies evolved over time, and creating the universe that we see today. So this just shows, I mean, maybe we don't have to show the whole video, but like they do these simulations that show, they simulate galaxy formation. So this is, from time after the Big Bang. These are very long time scales. Cosmology deals with usually it's like, most of cosmology assumes like above a megaparsec of scale and distance, which is 10 to the 19 miles. I mean, it's a huge amount of space. Also a very large amount of time. But they run these simulations that show basically how the structure of the universe formed. And basically, if you have dark matter in the simulation, I think something in this, I'm not sure exactly what the color scales mean, but it's supposed to show you how, like, dark matter is basically the glue that kind of helps these galaxies formed as, you know, the universe evolved over time. And these simulations match up better to what we see in the universe if you have dark matter in the simulation. It looks cool when they, yeah, this view kind of shows a spiral galaxy. Anyways, but so there's a lot of evidence. Let's see if I can skip over that dark matter exists. So I talked about rotation curves. I mentioned simulations. There's also been gravitational lensing measurements, or this observation of the bullet cluster, which was two galaxies colliding. And they were able to kind of tell that there's a different distribution of where the mass is as opposed to the gas that was emitting X-rays. There's a mountain of evidence that we need, you know, a new particle, or need to, you know, step outside of the standard model. Sometimes they talk about extending the standard model. So you might have heard of like supersymmetry. If you add, you know, some other particles, there might be particles that behave like dark matter. But evidence from cosmology says that this is us, everything we know, all the stars, you know, so that it's only 5% of the energy content of the universe. So, you know, when you hear there's like 5 times more dark matter than ordinary matter, that's basically the relationship between these two pie charts. Dark energy, I won't get into, but we do have a talk about cosmology later in the term that will talk more about dark energy and how that was found. But the question is, what is dark matter? I mean, so we have the standard model of particle physics. It explains things very well that we see at particle colliders. But there's still some discrepancies from astronomy. But there's no particle in the standard model that behaves like dark matter, which I'll tell you the requirements in a second. But there's a lot of hypothetical candidates, you know, dark matter candidates that arise from extensions to the standard model. So maybe if you know, add a new type of particle, or, you know, add a new term to the Lagrangian or whatever, and you can, and maybe that particle would have the qualities of dark matter, and often sometimes they might solve some other problem in physics. So that's, talk about that if you have. Okay. But I like this picture because it's like, this is standard model, and then there's this big blob of unknown stuff that we're trying to figure out, you know, what it is, what it could be. So there's 3 main ways that we search for dark matter. So this diagram, I showed it here, but this is kind of encoding like the interaction. So there's 3 ways you can search for dark matter. Well, make it, shake it, break it, they say. So this is make it. The particle colliders. So basically the idea is you create some beam of particle, you create some really high energetic collision, and then you try and reconstruct, you know, using those crazy particle tracker detectors and calorimeters, electromagnetic calorimeter, hadronic calorimeter, use that to reconstruct all of the energy deposited in that collision. And then you basically are able to look for missing mass, or like, you know, neutral particles that escaped your detector, and you're able to set limits on where dark matter could be based on looking for missing mass in these collisions. So that's make it. So shake it is like direct detection experiments. So basically, you know, the dark matter comes in and scatters off your detector. So going this way, if you kind of think of the diagram, we have a standard model particle and a dark matter particle. So dark matter particle interacting with the standard model particle. It scatters, kind of keeps moving, but deposits some energy with your standard model particle, which could be xenon or argon, or, you know, in my case, we use silicon. But you have to assume something with all of these. So in this case, you're assuming that the dark matter interacts in some way with the standard model, which is an assumption. There's always got to be some assumption that, you know, that you make. And then so for indirect detection, this assumes, so this would be annihilation. So you have 2 dark matter particles. A lot of these dark matter candidates, they're their own antiparticles. So they can annihilate with each other if they happen to find each other, and they produce, you know, depending on your model of what the dark matter is, they can produce gamma rays. So Fermilab is a space telescope that detects gamma rays. IceCube, they can produce neutrinos. AMS, I worked on GAPS for my PhD, and AMS, they both look for cosmic rays, so like antiparticles or charged particles from space. They don't make it through the atmosphere, so you need to have a telescope or a balloon to detect them. So yes, make it, shake it, break it. The 3 ways we search for dark matter. Most of what we'll talk about is the direct detection, today, because that's a lot of what Fermilab does. So anyways, there's a lot of theoretical candidates that could be dark matter or have the qualities. The qualities, I mean, are gravitational interactions, no stronger electromagnetic force, otherwise we would have seen them. Non-relativistic or cold, that's something that comes from those simulations. Won't get into the details. But also stable on cosmological scale. So usually the assumption is this dark matter has been around since the beginning of the universe, and it's still around now. It's still exerting gravity on things, so it's still out there. There's a lot of different models covering a lot of different mass range. I'll talk about why we talk about dark matter mass in a second. The crazy amount of mass range. Ryan will talk about, like, how do you choose where to look when you build a detector? You have to choose a certain energy range that you're going to be, design your detector to look at in a certain mass range. Because, well, there's two things. So this energy density tells you, it's basically like, you can think of it as like mass density or energy per volume or mass per volume. I guess that would be more as, akin here. But so depending on the mass of your dark matter particle, so this is a measured parameter from cosmology. So that's a fixed parameter that we know that cosmology tells us is the right number. And we believe it, we trust it. So depending on the mass of your dark matter particle, the number density, or the number of dark matter particles in this room, for instance, will be up or down. So the lower the dark matter mass, the higher the number density of dark matter, and vice versa. In fact, like when you go so low below an EV, it starts becoming wave-like dark matter. So the dark matter, there's so much dark matter in the room that you start getting wave-like phenomena. Or the Broglie wavelengths overlap, and you start getting wave-like phenomena. But I won't get into that. So, but the point is, the mass of the dark matter particle depends how you design your detector to do that sort of search. And usually, or most of the stuff, well, that I work on, and I think that Ryan will talk about, I don't think you're going to talk about axions at all, assumes dark matter scattering. So this is a dark matter particle. It comes in, it scatters off an electron, it excites an electron, and then keeps moving. But this is, for direct detection, we're assuming that the dark matter particle interacts, deposits some energy, and then we're able to, collect, we're able to see this energy deposit, but also discriminate it from other things that deposit energy in our detector. Because, right, our photons, our electrons, all charged particles are there's going to be a lot of backgrounds, in our detector. So we have to find ways to identify, discriminate a dark matter event from, a background event. But this is the main schematic. But the biggest thing is that in general, so for talking about the mass range, like, a heavier dark matter particle will deposit more energy than lighter dark matter. So if you think about, like, a bowling ball compared to like a golf ball or something, the bowling ball is going to, deposit a lot more energy. Or if we have the tennis ball crystal here, it'll shake things up a lot more shaking than you get from, yeah. And that is my last slide. So I think I'm pretty good. Although probably want to. Maybe 20 minutes, Ryan? How's that sound? Just start the panel on time. Hope I didn't go over. One sec.
All right. So thanks, Nate. So let's talk a little bit more about dark matter direct detection searches. And yeah, we're going to talk about the searches where we look for scatters of dark matter particles. And the real plot to look at, one of the important plots to look at if you're in the fields, right, is this thing. And it's really complicated. Let me make sure I find the laser. Right, it's really complicated, but we're going to break it down. So on the x-axis is the hypothesized dark matter mass. As Nate said, we don't know what it is yet. So depending on how large it is, if it's larger, there are fewer particles per cubic volume. If it's smaller, then there are more. And then on the y-axis, this is the dark matter nucleon cross-section. So basically, if you think back to the first few slides that Nate showed, it's basically very similar to the probability of interaction in your detector. So if we go higher in this square, it means we have more likely interactions. And if we go to the right, it is stating that we have if we go up and to the right, we have more likely interactions for a larger dark matter particle. Now, the curves here represent different experiments' ability to probe this space, right? So, for example, I guess it's xenon and xenon 1-ton curve here, the yellow one that I'm trying to follow. When you do a measurement, you map out a curve and you say every point in this space above that curve is no longer allowed, right? Because we do an experiment, we don't see dark matter, and if the dark matter interacted this frequently, we would have seen it with that experiment. So you basically kill all of the models that are above a certain, above your curve. So that's kind of the way to look at this plot, right? And then you can see it's very congested. There's like, dozens of, a dozen or two experiments that are all competing. The dashed lines are projections and the solid lines are actual measurements. And so this is kind of the space that we're looking at here. Yes, question. Yes. So the neutrino fog is a background that we're going to hit as we scale up our detectors even further. It's basically a background from a number of different sources. If you're over here, it's like solar neutrinos. If you're here, it's atmospheric and supernova neutrinos. But they basically make it impossible to, or significantly harder to confirm dark matter experiments down in this space. Yeah, great question. Okay, so let's keep moving. Our current best detectors to look for dark matter in this space are, to look for heavy dark matter, or the scattering, are xenon time projection chambers, or TPCs. And they're very similar to the argon TPCs that we discussed in the previous talk. But I want to kind of give you a little bit of a sense of what these look like. So this is the LZ experiment. This is what I worked on, what Dylan and I both worked on for our PhDs. It is basically a big tank of liquid xenon. This time it's xenon, and I know someone asked about argon versus other nobles. Xenon, we use xenon, and there are a number of reasons why we like it over argon. We can talk about that later if you want. But basically what we do is we wait for an interaction. When we have an interaction, we get two signals. We get a little burst of light that's immediate, and so that ricochets around and hits our, we call them photomultiplier tube arrays. So this is one of the arrays. I think this is the bottom array here, and then there's a top array up here. And then we also get some electrons, right, from ionization. And that ionization is drifted up to the top of the chamber and converted into a giant burst of light, a second burst of light that we can also see with our PMTs. So by looking for both of these bursts of light, we can look at events and try to kind of sift through what's dark matter and what's not. Another important thing about this is that this detector is kind of the meat of the experiment, but it is surrounded by kind of a bunch of layers like an onion. So there's a bunch of there's some scintillator layer here. There's some water tank around that, and then this whole thing is about a mile deep in South Dakota, and actually a very like a location in the mine that's next to where the Dune experiment is going to be. And this has been running for a couple of years now. So this is just kind of, you want to do that so that you can exclude as much background as you can. You want to limit as many potential boring, like normal physics events as you can, and look for those very rare dark matter scatters that may swing by. So just to go into a little bit more detail about this, this is same picture. This is an example of what you would see if you were looking at a signal in the detector. And so this is kind of the value on the y-axis is basically the summed amplitude of all the signals from all of the different PMTs. And so we see for an interaction, we see our first S1 pulse, and then we see our S2 pulse there. So this is the first burst of light, the electrons drift, and then this is the electrons being, producing a second pulse of light that you can see. And from these two things, we can actually estimate very interesting information about our interaction. So we can estimate X, Y, and Z of the location in the detector, whether it was like near the top or the side or the bottom or in the center where we really care about looking. You can estimate the energy deposited in the interaction, right? So if you have a larger pulse, then you get, that corresponds to more energy. And you can also look at the type of particle depositing the energy, right? So if you look at the ratio of the integrals, or the ratio of the area of this pulse and that pulse, you can sift through whether or not this is from, say, an alpha particle, or a neutron, or dark matter, or an electron or a gamma, things like that. So there's a lot of really useful information that you can tease out of a waveform like this when you're looking for dark matter. in these TPCs. So this is pop quiz. Every dot on this plot is a particle interaction. Can you tell me which ones are dark matter? Yes. So the space in between them, every dot is where one interaction happened. Oh, sorry, I should have explained the plot first. So this is basically the distance from the center of the detector in R, and this is the like height of the the height of the detector. So the top of the detector is up here, the bottom of the detector is here. This is the center of the detector, and this is the edge of the detector. So now I will re-ask that question. Yes. Blue circles. Not so much. So it was sort of a trick question. None of these are dark matter because we haven't detected dark matter yet. But the important thing, right, so that highlights an important point, which is that all of these are from some other known physics, right? And so part of the challenge of doing dark matter experiments with these kinds of detectors is really understanding what all this other known physics is, right? If we take the blue circles, for example, right? These, I don't remember what the actual legend for these said, but basically when you're at the edge of the detector, near the top of the detector, you have like a region where there's some gaseous xenon and you get less, shielding from gamma rays. And so these are likely to be mostly gamma rays from other random stuff. Yeah. But then there's also neutrino events that are farther in and so on and so forth. And so you have to be very careful about what you claim is dark matter when you do these searches. Okay, so xenon is good, but it's really good for heavy dark matter in this region here. But as you go to lower dark matter candidates, you actually have to use a different technology. And I'm going to cover briefly, the CCD-based detectors that Nate was talking about. I'm going to kind of breeze through these because they're more of Nate's wheelhouse than mine. But basically, we need a new kind of technology because when you have a lighter dark matter particle, it imparts less energy into your detector material, which means that if your ionization energy for xenon is, I don't know, order 10 eV, 10 electron volts, you won't be able to see any dark matter particle that deposits less than that. But you can if your ionization energy is 1 eV. So we can look at how we use CCDs. So these again are basically a piece of silicon that has an electric field established across it, and when you bump into into some electron in your crystal, you can free an electron with if you have like order 1 to 3 eV, and then you can drift those across your chip and read those out using the same kind of technology that you do in your digital camera. So it's just we look for much far fewer events or far fewer interactions in these chips than you do with your digital camera, because with your camera you want to see a picture made of many photons, and here we really want to look for as rare interactions as possible. So one of the cool experiments that has run in the past here at Fermilab based on CCDs is Sensei. So this is a CCD-based experiment that's in some lead shielding down underground in the Minos Hall, and so there's it's about a gram instead of 10 tons. It's operated at cryogenic temperatures, and so they did some really interesting dark matter searches with this, and had world-leading results a year or so ago. Okay, but even if we like CCDs, they struggle below the ionization energy of say silicon, which they're made of, right? So how do we go to really low dark matter masses, like well off to the left of this curve? And the answer is that we can actually try superconductors and quantum sensors. So there's a new technology that you can use to go lower. So let's talk about those. And this is actually where Dylan and I now both work. So what are quantum sensors? They're sensitive detectors which are operated using the rules of quantum mechanics. So if you think about, and that's very generic. So we're not going to talk about all of the possible quantum sensors you could make, but we're going to talk about one specific type, which is superconducting qubits. So superconducting qubits are basically, we're going to start on this end. These are basically little LC circuits, little oscillators that act as artificial atoms. So if you think about atoms in the kind of quantum sense, the hydrogen atom, you have different states of the electron in the hydrogen atom, and you can make discrete transitions between those states. But that's like super tiny, super microscopic. We can actually make systems that show those same properties at a what we'll call a mesoscopic scale. This is kind of probably the cross here is part of that circuit, and it's about 400 microns across. So it's still very small, but it's not atom small, right? So it's something that we can actually make in a lab very easily, reasonably easily, and see with our own eyes. These qubits are patterned on a silicon chip. So this is the chip here. That silicon chip is again about it's still pretty small. It's about the size of your pinky. It's about a centimeter by a centimeter. That silicon chip. And the interesting thing about these, right, is that you know, they're very sensitive. But in order to be very sensitive, we need to treat them very carefully and put them in a very sensitive detector, a very sensitive environment, and a very well shielded environment. In a number of ways. So we basically have to put this chip on which our qubits are located inside some shielding here. And that goes inside another layer of shielding. And that goes inside another layer of shielding. And this is in what we call a dilution fridge, which takes it all the way down to 10 millikelvin temperatures. So it's very cold, very well shielded, and that allows us to actually operate these quantum sensors looking for dark matter. So how do we actually do the searches with those? Or sorry, let's get to that in the next slide. How do we operate these quantum sensors? We talk to them using RF signals. So this is something Nate alluded to a little while ago. This is a little diagram of one of our chips. You basically send a microwave pulse in. It goes down this feed line, and you read the pulse out. And in the middle, it will talk to the various little crosses, the qubits. And it can talk to those in a way that's pretty easy to read out using microwave electronics. And so this is a fun picture of some graduate students and Dylan and me behind the camera, seeing some resonators, seeing some of those microwave signals from our 6 qubits, you know, several months ago. Okay, so this is how we operate them. How are they actually interesting as a dark matter detector? What they can do is actually detect phonons or particles of heat. So we've talked about photons, we've talked about electrons, positrons, protons, all sorts of, you know, ons. Phonons are not true fundamental particles, but they're like little quanta of lattice vibration. So if you have a crystal that has periodic structure, you can get little lattice vibrations that propagate like particles within that substrate. And you know, suppose you have you know our chip, and you have a superconducting layer into which our qubits are etched. You can have a particle scatter in your chip, create some phonons. Those phonons can then go in and break some of the Cooper pairs that contribute to the superconducting qualities of that film. And then they can do some, they can quantum tunnel across one of the features in our qubit. And when they do, we can sense that. So basically, the goal is that these things allow us to sense phonons, which allow us to look at lower and lower energy scatters of dark matter, so that we're not limited by our electronic band gap. And this is actually a simulation of what this actually looks like for a couple of different injected energies. This just illustrates some of the tools and some of the strategies that we use to kind of study how we do phonon sensing. So this is 5 milli eV. So again, this is 15 orders of magnitude-ish down from what the LHC tries to look at. So very, very small energy. And you can see that if you inject a phonon into our chip, it'll bounce around a bunch and then probably peter out. But as you increase the amount of energy that goes into your chip, you can start to see that you just kind of like, you know, you have this wash, this bath of phonons, and some of them will hit your qubits and maybe, you know, give you a signal. But actually, once the phonons hit our qubit, how do we actually sense them? And the way that we can do this, one way that we can do this is actually with looking at errors in superconducting qubits. So if you're familiar with superconducting qubits, you may know that they're associated with the quantum computing industry. So you know they can be used for computation. And in that community, there's this language that if you have a qubit misbehave, there's an error, like your calculation undergoes an error, and you kind of lose some of the fidelity in your calculation or computation that you're doing. But these errors can also be useful because they can tell us that there's some interaction that happened in your chip, right? So basically, the way that we look for these errors is that we say, okay, our qubit, we can put our qubit in the 0 state. It's a kind of like a 2-state system, like a bit sort of, but it's a little fancier than that. You put the qubit in the 0 state. You send in a microwave pulse, and that converts it into a 1. And then if it's in the 1 state and you have some interaction, it can actually drop back down to the 0 state. And by looking for the times when it drops back down to the 0 state, and this is what we call an error. So by looking for those moments when it drops back down to the 0 state, you can actually kind of look for those interactions in the substrate. Is that 5 minutes? Okay. And this is actually what people have done. This is a plot from a Google superconducting qubit group, where we basically, on the x-axis is time, some arbitrary time that they're looking at. On the y-axis is a number of simultaneous qubit errors. So they have something like 53 qubits on their chip. And at some point, there's some baseline of errors that happen naturally because qubits are not perfect. But then at some point, like 23 qubits all see errors at the same time. What is going on with that? And it's basically, right, you have some cosmic ray or something rip through your chip and create a bunch of phonons in the substrate that then bounce around, and then they hit all of the qubits on the chip, or 23 of them or whatever. And then over time, that heat kind of dissipates out to the fridge, and so you see that the errors go back to baseline. But in this whole process, you get a pulse, which is what we like to see in particle physics because it tells us, hey, something happened right here, right now. And then we can accumulate those over long periods of time and study them in the same way that we studied things in liquid xenon TPCs. Okay. So between TPCs, CCDs, and quantum sensors, we're done, right? That's all. We've studied all of potential dark matter space, right? Okay. No, I see some heads shaking. That's what I was looking for. Thank you. Yeah, the answer is no, and we really have only carved out a small part of this, right? And that's also saying, we really haven't carved out a whole lot of this space even on its own. But the main point is that there's something like 80 orders of magnitude of dark matter mass space that we need to search in, and no one detector type can do it. Right, I've just shown you 3 different detector types that are all very different in, what materials they're made from, how they're operated, and what kinds of backgrounds they might have. And that's only in this kind of range of a few orders of magnitude in this particular spot in dark matter particle-like scattering space. So there's, as Nate said, there's lots of orders of magnitude to look for dark matter down here. Underneath this overlay here, there's another several orders of magnitude that way. And so the field is really just kind of in this, this search mode where we're trying to figure out where it is and building a whole bunch of different types of detectors. Maybe the detectors look a little bit more like a radio over here. Maybe they look a little bit more like a, xenon tank of xenon over here, right? So things will be different depending on where you want to look. And maybe one of you will be the one to get the Nobel Prize for finding it, right? Who knows how long it'll take? Maybe we'll see it tomorrow. I don't think we're going to see it tomorrow, but maybe we'll see it in 10 years or 30 years or something, depending on, who comes up with the next coolest idea. So that is it. Happy to take questions now, and thanks for listening. Yeah. All right. Do we have any questions? Yes. Let me find the mic, actually. Thanks. Hello. Can people online? That one's good. Okay.
Thanks for the talk. I don't have a question, but maybe just something to add to the excitement of dark matter, which is that we don't we don't know for sure that there's only one dark matter candidate. So even if we
Right.
find something, there's still a lot to find. Like, we don't know if it's one particle or a bunch of things. So just want to put that out there. There's like a huge opportunity for science to do with dark matter.
Right. Any other questions? Me on Zoom. If they're not, I can make one other comment. Yeah, I can make one other comment. So we were talking a little bit about other liquid noble-based detectors. So xenon's very interesting. Argon and xenon are both interesting for dark matter. Xenon is interesting in part because it's denser than argon, and so you get more of a shielding effect for the central volume. So you can shield gamma rays and stuff better with the outer layers of xenon. It's also nice because each of the different noble, noble elements have different levels of intrinsic radioactivity. So like the nucleus of that atom can have many different isotopes that some of which are radioactive. And for a good dark matter detector, you want as few of those radioactive isotopes as possible. Argon has one that's kind of in an annoying, like that's present to an annoying level. Xenon has fewer. And so that's another reason we like xenon. There's like 3 or 4 different reasons we like xenon. But one additional thing to think about is that in terms of radioactivity, as you go further down in the periodic table and start probing things like radon, radon is very it's not reactive, it's very unstable. And so it will decay. And so if you were able to get 10 tons of radon into 10 tons of liquid radon into a chamber, I mean, I don't even want to know what would happen, but like basically you and the detector and the facility and probably that state would glow for a while, right? It's very like, A, it would be challenging to do that, but B, it decays all the time. So. Question? Yes.
This is somewhat unrelated, but you mentioned glowing. But so I know you said that as a joke, but what comes off, like, because I've heard of uranium glass being used before, what comes off of uranium glass that goes into our eyes that makes it glow?
What comes off of uranium glass that comes into?
You had the chart of our eye before, and you said things have to physically enter our eye. So does it give off green light? Does it? What happens there?
So I don't know specifically what the like how you get from the decay to the green light that you see. I mean, it would give off photons of 500 nanometer wavelength or whatever green is, right? To get to that point, there's probably a step or two where you have a decay of something, and the decay of something excites the material that the uranium is contained within, right? I'm assuming it's not pure uranium, so there's probably something that will fluoresce, and that fluorescence will, the excitation of that material will then allow it to de-excite and emit that radiation, or the photons that you see, something like that. But I don't know specifically what material you're talking about. Yeah. Great question.
Quick Google. So uranium fluoresces under UV light because UV excites the electrons above the ground state and gives off photons as electrons transition back to the ground state.
It's uranium fluorescence itself. Okay, I didn't know that.
Excite between energy levels, I guess.
Great. Okay.
Yeah. Well, electrons hopping around basically, and that converts to energy. Right. Okay, so we have a panel discussion. Let's take 5 minutes and begin around 11:10. So we have enough time to get set up. I'll plan to wrap up around noon, but we'll stick 5 right now and just get everything set up. We're back. So thank you for the patience. Just had to get some things set up. So we have a panel of 4 speakers here. Whoever wants to hold it. I should have prepared introductions, but I tried to we have an array of people. So, well, maybe you all can introduce yourselves. So there's two panels that we're doing. The idea is this is about your path to becoming a scientist. So maybe you can introduce yourself, talk about, what your current position is, and we can start from there. And then maybe we can talk about your roots a little later, and then we'll go get questions from people on Zoom if you can monitor it, and people from the room, just raise your hands and we'll try and get a mic to you. So please, yeah, go ahead, Carrie.
Hi, I'm Carrie DiPetrillo. I'm a professor at the University of Chicago. I work on the Atlas experiment. I actually did my postdoc here at Fermilab before I came to Chicago, in the area for a few years now. My name's Anna. I work on the Icarus experiment. I'm a graduate student, so I've been based at Fermilab for almost 3 years. So.
My name is Jason St. John, he, him pronouns. I work on machine learning and the particle accelerators, although my upbringing was like these folks as a detector physicist.
Hello, I'm Jamie Dyer. I'm a graduate student. My university is Colorado State University, but I'm based at Fermilab now. And I also work on the Icarus experiment.
I guess I'll start with the first question. Well, where'd you all grow up? What kind of drew you to physics or science when you were coming up? So we have you don't have to do your whole biography, but we have 45 minutes. Okay, so yeah.
I guess we can bounce back. Okay, so I am from Logan, Utah originally. I did my undergraduate studies at University of Utah. Obviously, I majored in physics. I got really involved with undergraduate research at the University of Utah. I was mostly doing like quasar astrophysics, and it was sort of in the context of cosmology. And then I actually had a bit of a nonlinear path coming to graduate school. So I took a couple years off of school before I came to graduate school. I kept doing undergraduate research like after I finished my bachelor's degree, working in that same research group for about 9 months. And then I did a bunch of non-physics stuff. I wasn't sure that I wanted to be a physicist, and so I took some time to like explore other avenues, and like traveled around a little bit, had some adventures. I then got a job in a laboratory in my hometown, and I was able to do some science, but it was just like not really scratching the itch. I felt like the tasks I was doing at that lab were not like kind of the rigor that I was craving if I was going to be like in the world of science. So I decided to apply to graduate school, and that has worked out so far. Haven't finished yet, but yeah, that's kind of how I arrived at Colorado State University, and I'm working up.
Cool. I grew up in Nashville, Tennessee, and was a nerdy little kid. In 7th or 8th grade, somehow I stumbled across like the subatomic particles in an encyclopedia, which is like the Wikipedia, but it's printed out. And they didn't quite make sense to me. They didn't cohere, but I was interested. And then ended up like for a science fair, I did a thing where I just like learned more about it and tried to lay it all out. So I always liked particle physics, I guess, and kind of knew that was the name for it. But just generally wanted to get into science. So then I did undergraduate at Harvard, where I was like, this was not great. I'm not sure I want to do any more of this. And I got a job, but I got a job in the area at Boston University's physics department. I always liked doing theater stuff. It was one of my fun, like like stay up all night with people doing that kind of stuff. And this was sort of an aspect of that because I was the lecture demonstration specialist, meaning I had all the cool toys that the professors used to like show things exploding or, catching on fire or electrical stuff, moving things around. Super fun. But I was really close to academia there, and I got sucked back into it. There were free classes. So I worked there for 3 years, but my whole last year, I was also taking one graduate level introductory class. I started with the one that I thought I would like the least. and which was statistical mechanics and thermodynamics. It was like, this is terrible. This is nothing like what I want to do. But I got an okay grade, and it really wasn't that uninteresting. It was kind of cool. So I committed. I didn't apply to other universities, which maybe I should have, but I enrolled in the graduate program there full time the next year. And I also wandered around there. I started off in solid state physics, meaning like, materials and layers of things. But then I took a summer class on particle accelerators, and I thought, man, I really want to go back to that stuff. So I had this whole like coming out with my advisor at the time was like, it's not you, it's me. I've always been a particle physicist. I just know who I am. And I joined the CMS group, which is the rival to Atlas. It is far simpler and better. And ended up here. And then even here, I've been wandering around doing what I was doing. So my graduate work was here on CMS, and then my postdoctorate work, which is like, you've got a degree, but you're not a professor. You can just do some research for a little bit and build up your things. And I switched things to do liquid argon time projection chambers here because all the cool kids in the cafeteria were doing that. And I got a job with the University of Cincinnati, which kept me here. They were paying me, but the work was be here, do this research, keep us up on it. And I got a job with this lab directly, which is the job I have now.
Cool. So I actually never took a physics class in high school. So I came into undergrad honestly barely knowing anything about physics. I always really liked math. So I really like math. I really didn't know what I wanted to do with it. I didn't know what I really could do with it. So I thought maybe I would do engineering, maybe I'd be a math major. And then my sister said, you should take a physics class. And I'm like, oh no, people say that's really hard. And she's like, but it's a lot of math. And so then I took a physics class. That was pretty cool. And then I was a freshman, so I was applying for summer internships and stuff. And I got a really cool internship at the Sudan underground mine based in northern Minnesota. And so they have, now it's decommissioned, but they had a huge particle accelerator there. And it was half a mile underground. So my job was bringing people underground and trying to explain the particle physics we do there without having much of the background. But it just really opened up my eyes to this like really amazing world of particle physics, and it just wowed and amazed me. And so that was really cool. And so after that summer, I switched majors to physics, and I kind of just kept going with it. So I feel like I kind of tripped and fell into physics, but I wasn't ever really planning for this. I didn't know anything about this, but it's worked out really cool. I think there's just so much you can do in this field, and you truly never have a boring or same day. Every day is different. So yeah, it's been exciting and not so straightforward path, but.
So I grew up in the Providence area, so Providence, Rhode Island, small state. And I think in my family, no one really did physics or academia, so I didn't know what physics was until I took it as a senior in high school. And even then, it's mechanical, old physics. And when I went to college at Brown University. I applied there because they had a really strong neuroscience program. So this was very much in sort of the theme of my family likes science. They think it's biology and medicine and stuff like this. So I thought I was going to do a neuroscience undergrad and then apply to be a doctor. And part of the requirements for the neuro major were taking physics and chemistry classes, and I liked those a lot better. But I did them my freshman year. I didn't think I was going to switch. I thought I would do the neuroscience major. And when I stopped taking physics, I really missed it. So I came back in my sophomore year and rejoined sort of the typical physics course sequence and wound up switching into the physics major end of my sophomore year. I did summer research in a lab at my university, a biophysics lab, because that was kind of like the preparation I had had up to that point, and it seemed like midway between neuro and physics. So I did a biophysics major, and I applied to graduate schools. I decided to go to Harvard because they had a really strong biophysics program, And I kind of did the same thing where I like took courses for biophysics and tried a biophysics lab, and it just didn't, it became further and further away from the kind of physics course I was taking, and I was really driven. Biophysics is tough because when you're doing a controlled experiment, it's so sensitive to many variables and the system that is around it. It's very hard. It's actually very difficult to get repeatable results. Impressive when they do. But I was really trying to go smaller, more fundamental, the most controlled experiment you could possibly have, which if you sit and you think about it is really particle physics. It's, you collide protons at nearly the speed of light, and you can predict with great accuracy what's going to come out, and you can make very powerful statistical interpretations about what happens. So that was kind of why I was drawn to particle physics and wound up switching into it end of my first year. And I did my PhD on the ATLAS experiment. It was run 2 of the LHC, so I spent 4 years at CERN working on operating the muon system and doing a thesis analysis where I did a search for new physics. For my postdoc, I had spent all of this time operating a detector system that someone built, and that was kind of older technology. Like the technology for the muon systems was invented years ago or more. So I wanted to learn about silicon detectors. A lot more rapid development that's happening in that area. And Fermilab was really is probably one of the best places to do that in the US. I don't know if you guys have seen the silicon detector facility that they have here yet, or if you
SciDet tour.
Yeah. Yeah, so I spent a lot of time in SciDet doing silicon detector R&D. So not just like really precise pixel detectors, but also 30 picosecond. And inputting sort of the information from those measurements for a timing layer. So I switched to the other side of the ring, and I have opinions about which parts are more simple or less simple. And I continued searching for new physics. As a postdoc, I kind of felt like I had all of these ideas and none of the resources to execute them. Like you don't have your own money and your own stuff. So I really wanted to be a professor. I applied to jobs on both Atlas and CMS, and I went back across the ring. It feels good to be home on Atlas. And I've been a professor for about a year, so I'm still early in the growing the group and building the lab phase, but it's been a lot of fun.
All right. I think now I can, what do you all want to know? Questions you have, or I can keep chiming in. I see a hand switching, catching.
So what does, so you work on these projects and you work at Fermilab, but what does like what are you physically doing during the day? Are you doing programming a computer? Are you working in a lab? Are you doing math on a piece of paper? What's happening on a day-to-day basis for particle physicists?
I will say our panel next week is specifically on everyday life of a physicist. But we can get short answers, from the panel.
So, okay, so what they say being a professor is supposed to be is 30% teaching, 30% service work. So this is like actively helping, viewing other people's papers to make sure they're correct, organizing seminars in your department, so some like spreadsheet type stuff, and then research, which is a little bit different because this could be applying for funding to support your students to do research. It could literally be sitting down and making plots and coding in Python, or tinkering in the lab and building a setup. But that's the rough breakdown that people recommend. The reality is that you get a lot of like 10 to 15 minute periods to do those different tasks, and you're rapidly switching between them. It's a lot more managing in soft skills, I think, than a postdoc or a PhD was, where in my PhD, it was all research almost. In terms of what the research looks like, I really like working on the Atlas and CMS experiments because it's a really nice mix of sitting and coding and doing analysis, tinkering in the lab, and talking to people about what the right next steps to do are, what you found out, sharing the lessons that you learned from your work. So I kind of like the nice mix of things. As a professor, I wish I had maybe more than 15 minutes at a time to do anything, but it is what it is.
Well, I think my day-to-day life has really changed throughout my degree. So when I was an undergrad and just starting out in grad school, my day-to-day was taking classes, doing coursework, mainly just solving problems, pen and paper. And after moving out to Fermilab, I started with more hands-on stuff. So working on the Icarus detector with hardware, and so tinkering with things, and so that's kind of fun. And now that our detector is pretty built and stable and we're running, now I'm doing more coding and analysis. So a lot of stuff on the laptop and writing code and doing analysis with software there. So kind of a mixed bag.
There's a ton of what I end up doing every day is talking to people, because while it is fun and necessary to write the code and stuff, but deciding like what should the code do, and then once you think it's working, people will ask you good questions about like, how do you know it's working? Like really, and after a while you get good at asking yourself that question and like making the checks, and you're like, so now when you present a thing that you've done, say, and I know because, right, and you show that stuff. Have more criticisms usually. But it's a very communal effort. There's nothing that we do alone. And the more that you have, the more voices you have in the room that are contributing useful feedback, even if it's a critical nature, but often it'll be like more ideation, more things to throw at the process. That makes a big difference. So I definitely have spent wonderful like afternoons, especially as a postdoc, like building the detector, checking out all of the pieces, literally like assembling the pieces in suit, and then like doing surveys to make sure we've got them aligned the way they need to be, filing all that information and back. But also there's always this stage where it's got to be discussion, and yeah, so I end up doing a lot of computer programming because my current undertaking is all machine learning stuff, but I also read stuff and then talk about it with people. I go to journal clubs so that people can talk about what they have just learned that's cool and interesting, and then we end up coming up with the next cool thing that we want to do. Or maybe we realize we should scrap what we're doing because it's not a good idea. People have shown. Right here on that.
Okay. So I am PhD. I do like almost entirely software stuff, so I don't really work too much on hardware. 100% of my time, other than meetings and discussion and talks and stuff like that, is spent like on my laptop. But I feel like coding can be used as a blanket statement a lot. So maybe I can say like the types of coding that I do, because there is a lot of variety in like what I do on my computer. So I work in kind of like 3 areas of coding. I work on a lot of simulation stuff. So that's like thinking about physics and figuring out how to put it into a code so that the code will output data or fake data, right? You're having the computer make up data based off of expectations that you have from some physics model and a detector model. So I write simulations for that, and then we can use that fake data to compare it to real data and just get a better feel for what's coming out of our detector and how well we actually understand that. I also work on software development, and so what that means is like we have this operating detector, but we need to be able to like babysit. That sounds like a condescending word, but I don't mean it to be condescending. But we need to be able to like manage our detector and check on it and make sure it's operating correctly. And so we can digitize that by building software that helps you do that, so that you don't have to be in the building to make sure everything's going okay. So I'll design software that will look at digitized data from our detector and tell you kind of like the status of how things are looking. in a user-friendly way, so that maybe a collaborator like in Europe can also take a shift monitoring the detector and be able to catch things if they're going wrong or respond. The third type of coding that I do is analysis work. So that's actually looking at data and coming up with really fun ways to like extract information from that, right? So getting data, of course, that's like a huge deal. You need to build a detector and you need to have data, but just getting the data doesn't tell you what's going on with nature. So it's really fun. I get to exercise a lot of creativity in the questions I ask and how I use code to kind of like probe the data for that.
Yeah, I'll keep stack. I think Jason's question, well, I think it's a good one. The suggestion was about, well, say you were to say you had a room full of high school students and they wanted advice on what what steps they could be taking now, or what they could be doing if they wanted to become a physicist, like any advice or things you learned on your path, bridging the gap from high school to what steps can they take now, or what should they be thinking of over the next 5 years if they want to do a career in academia.
Okay, this is like maybe really generic advice, but someone told me this once and I was like, wow, that's groundbreaking. But it's so simple, but just keep doing what you like to do. Like if you like doing physics, find ways to do that. And as long as it's coming from a place of like enjoyment and you keep pursuing that, then you're going to keep just very naturally becoming more and more qualified for the things you like to do. So it's really simple and generic. I thought it was kind of like when I heard that, but if you like physics, just keep doing it, doing what you like.
For engineering, how many engineers or possible engineers, maybe? Okay. A lot of the people I work with are engineers. Seems like we all love problem solving and getting things to work. It's so satisfying getting a thing to work. But I feel like the engineers are the people who have no patience for, but what else could we do? And what's the reason for the scientists are like, that is what I want to work on too. And anyway, either way, internships and like summer things are great. Like having professional contacts in the academic or engineering world, however you want to think of it, that is in the direction you think you might want to go. It'll help you learn a lot about how you feel when you do this stuff, and those people can help network you into this thing. Not the case that everyone applying with zero prior experience is going to be equally capable of writing the essay the way that they would like you to, right? And presenting yourself as the sort of person who would be accepted to whatever next step or helpful program or whatever you want. Whatever help you can find, and you can do research on your own to see what's out there. Fermilab has internships, but a lot of places do. Those things, I'm only naming internships because it's
Yeah, I guess I don't have too much to add, but mainly internships and just keep working hard, and if this is what interests you, and yeah, follow your passion.
I mean, the groundbreaking advice is like the first time you hear someone say, just do what you like to do, it's mind blowing. Don't do things that you don't like, or at least not for long periods of time. So there are two things that I think people don't usually say at this kind of panel. The first is this is kind of a theme in a lot of what we said in the first question or second question of how we got into physics, which was that we didn't know what physics was, or we didn't know how to get there. I think a lot of what people wind up doing for the rest of their lives is a coincidence of who you happen to talk to. So the best way to sort of open up opportunities for yourself is to just talk to people about what they do. So you're hearing about a lot of particle physics, accelerator physics today and through Saturday Morning Physics. But anytime you get a chance to talk to someone who has a real job, talk to them about it, learn what it's like, learn what their day-to-day is like, learn about what drives them, learn about what they enjoy, so that way you can decide for yourself what you want to do. So that's the first thing. The second thing is, I mean, internships are great, but also get a real job. Like, scoop ice cream for a summer or sell clothes. Working in the service industry teaches you how to optimize your time well, how to prioritize tasks, how to deal with people who are difficult. And this will serve you well in anything you do. And so even if it's just for a summer, it makes a big difference. Like I can see a difference in the students who come and want to work who have had a real job and who have never worked a regular job a day in their life. It will take you far if you learn how to deal with people like that.
I'll just add, you don't have to know what you want to do. I mean, it's the random walk or falling into physics. Like, I think when I was in high school, even when I started college, I was wanted to be a doctor. My mom's a doctor. I wanted to be an orthopedic surgeon. I played sports, wanted to be like a team doctor for like and I was like, do I really want to, I don't know, operate on people? I kind of like detectors more, and I don't know, just got the physics bug.
Shove bones back into sockets.
Yeah. So yeah, you don't have to know what you want to do, but it's important to, keep searching and be open to other possibilities. And before I'll pass to the next question. Well, when I was preparing the talk, I was looking at Leon Letterman talking about who started the Saturday Morning Physics program in the 80s or something. The goal isn't to get people into physics, but it's to basically teach you how physicists think and to, educate you on how particle physicists think to, create a more educated populace. So we don't expect you to be physicists or engineers. We'll definitely encourage you if that's what you want to do. But the goal is to steer you on a specific career path, but definitely to encourage you to, follow your dreams. With that said, I believe you had a question.
So I'm assuming you don't just sit in an empty room with a laptop all day, but more importantly, how do you interact with others throughout your career? How do you communicate with other physicists, or like what do you do with others? Do you just do work by yourself, or is it more of team things?
Yeah, so I think it's a really healthy mix of collaboration. Okay, so I can talk about this in the context of an ATLAS and CMS type experiment. There's 3,000 physicists. There's a hierarchy sort of that keeps the experiment running, starting with the spokesperson, and there will be people who sort of are in charge of the physics analysis or the physics analysis program, people who are in charge of calibrating data, collecting data, and designing and building upgrades to the detector itself. So there's some formal structure that helps keep the collaboration running. Do I know and interact with all 3,000 people on a regular basis? No, I do not. But I do interact with a subset of those people who work on things that I'm also interested in and who I've kind of like clicked with. People who, it's like, oh, you have a slightly different set of expertise than I do, but we're both interested in the same kinds of questions. That seems like it's going to be a really great collaboration. So I have like physics friends, actual friends in the collaboration who we're constantly thinking about how to do better physics, how to do better science. And sometimes we're directly working with each other. Sometimes it's like, that's a great idea. I'm oversaturated right now. Let's put a pin in it and come back to it in a few months kind of thing. So they're in the ATLAS collaboration. That's kind of how it works. Then there's usually some kind of a working group structure. This tends to be like order 5 to 10 people. It might be a few professors or lab scientists sort of heading the group and steering, a postdoc or postdocs kind of doing the more day-to-day supervision, and a lot of graduate students actually doing a lot of hands-on work. So that's also a structure that happens. I also interact a lot with people in my department in other areas of physics, so other faculty in other areas of physics, teaching students who are physics majors and who are not physics majors, so teaching them. So I am actually rarely, even though my office is a laptop and it's just one desk, I am rarely alone throughout the day. And I'm rarely physically alone throughout the day, and I'm also, when I am physically alone, I'm probably Skyping or Slacking somebody. So it's very social.
Yeah, I'd agree with that. I feel like a lot of time I spend either in meetings or messaging people. And so we have this, we use this app called Slack for a lot of experiments to just message people on, but constantly we're asking questions over that. If people are also here at Fermilab, that's one thing that's really nice about being here at Fermilab is you have other colleagues right down the hallway. And so a lot of experiments are kind of based on different floors here at Fermilab. And so we have like a wing where, you know, Jamie and I's desk are near other people who work on our same experiment where we can easily go knock on their door and ask. Yeah, and so it is like, I do spend a lot of my time alone at my desk, but also sometimes in meetings reaching out to people. But yeah, it's continually talking to people online. And
It is, yeah. So I can add to that. So my office is not in this building. The accelerator complex out around here, and the accelerator division, which is about 400 employees plus a bunch of contractors and other people we work with on a regular basis, all in different teams who have different responsibilities. And so just for an example, this week, a new person who's only been a year at the lab is working on a data collection problem for an AI application she's trying to develop. We have a thing which does this very difficult regulation of a power supply against the effects of other nearby power supplies that are larger. So it tends not to precisely hit the magnetic field we want it to hit when the beam is being injected into the synchrotron. The variation's small, and we have a system that's trying to compensate for that, but she would like to do better. The first thing she needs is a bunch of data on which to train some neural net. But it turns out it's really hard to get it. Like, you need to go talk to the control people, and they say, oh, you can get this data here. And we're like, okay, it's there, but the timestamps show that they're not at the right times. How do we figure out whether this is right or not? So we go into their technical spec and talk with them a lot. And then the other groups which tell us like how to process the data. We want to do a lot of computing. Now I need to go talk to the computer science people, and it's like, I need a whole lot of computers that can do this, this, and this. And what can we arrange, you know, temporarily, or do we need to go get some grant funding? I definitely have spent time filling out grant applications and trying to make a good argument for why the team that I'm putting together should be the ones who get the money to do this thing, because it's what the grant is trying to help support, all that sort of stuff.
Yeah, I would force kind of everything that's been said about like the interpersonal, like professional interactions, but then maybe take the opportunity to talk a little bit about more like personal interactions with other scientists. So of course, like we're all professionals here, and it's really important to maintain those professional relationships. We're also people, and it's easy to make friends here, and it's a really cool thing to be a part of the science community, especially like at Fermilab. I think there's just a really strong sense of community here. There's a user center where we can go and like play ping pong and sit on couches and just talk and visit after work. And it's not, you know, just talking about work all the time either. You know, we share that, we share science, and so it's comforting to have this group of people who's, you know, your peers professionally you can relate to. But you can also talk about, you know, things that happen at work. Maybe you're not talking about like the actual data analysis when you're just hanging out on a Saturday, but you do get a nice group of people who, you know, you have similar interests in science, but they're also peers, and sometimes we'll go to movies together or do things that like aren't scientific at all, right? So there is like a really good communal aspect to being in physics as well.
You point out to me, I also have spent a lot of time outside of working hours, like playing with kids that are friends, you know, that families that get together here. Or in fact, there is a daycare here because there's so many of the scientists here who like need a place for a kid who's not in school yet to go. Big community. It's also cool when you recognize someone as another particle physicist, like in an airport, right, or just in a cocktail party, whatever. I don't know what milieus we were all in. But it's neat to be in a profession where you have a connection with other people in that profession. You all know sort of like what is the current cool thing or whatever.
So our field is very spread out across the world. So you can make friends, and then maybe you move away for some research project, and then maybe like a year later you see them in Italy at a conference, and it's so cool, right? Because it's like you have friends all over. start to build like kind of.
About programming, do you exclusively use Python? And if so, is there a reason why, like, instead of like any other language?
I mostly use Python, but definitely not exclusively. I think, yeah, it just depends on the project and kind of your research group. I like Python because I like its plotting mechanism.
I like Python because of the AI stuff. There are always new packages coming out, and it's open source, which is nice. But I've also spent time like doing radiation shielding assessments where all of our simulations for that, which are how we estimate how much concrete we need to keep public safe or whatever, that's all written in Fortran. So I had to go back and like learn Fortran. I had already learned C++, so that wasn't terrible. And I've also worked, of course, in C++. Our controls department is really getting into Flutter and Dart right now. So there are a lot of people doing Rust and Julia that I can think of. And databases, while they're not exactly a coding language, but they go beyond SQL and just pulling information in and out of tables. So all of that stuff has been handy.
I would say that it definitely depends, like your research experience, like group and stuff like that. I mainly use C++. I've found that that is a really good language to learn. Like just a lot of things in particle physics are like, I think there's a lot of C++. But the main thing is I feel like I first learned Python. And so I feel like if you can learn one language and kind of like understand that, that's really what you need. It's easy to like, okay, I know how to do this in Python. How do I translate that knowledge to a new language? It's kind of just, you know, more translating at that point. But yeah, if you kind of learn, it's mainly kind of training when you're learning, and maybe you guys already are learning coding languages, I'm guessing. But yeah, it's just training your brain to think in a new way. But yeah, I think C++, Python.
So like the real Atlas software is C++ with Python wrappers. So knowing C++ definitely gives you an advantage to those who just work in Python. It's closer to sort of what the computer is actually doing. It's a lot less loosey-goosey. It's also very important for data acquisition. Like I think almost all of our data acquisition software is C++. There's also a lot of firmware, which sometimes physicists learn how to write, or they learn how to write Python code or C++ code that can be translated into firmware. But that's something Verilog or VHTML, whatever, VHDL, early. Yeah, so there's, I think, a wide array of languages besides C++ and Python, but that's probably dominant.
I'll just add on. So, well, when I was in undergrad, I took first 100 level sequence of a computer science major where I learned Java. I don't use Java at all, but it was useful as far as understanding how to structure object-oriented programming. So that's like what C++ is. Python is, you can be more loosey-goosey in how you define variables and stuff. And a lot of stuff, most of the stuff I do today, I do with Python, but it's wrappers. So it's like you import the functionality of like some C++ code. Someone did all the work for me so I can write the code. But what else was I gonna say? Usually when you work in a research group, how it works, like if you were to work for me, or well, when I started grad school, someone handed me a code, not the best code, but it worked, and then here, change this or change this. And so you run someone else's code, maybe I picked up their bad habits. But usually, like if you're starting to work in a research group, someone will give you a code and tell you to make minor tweaks, plot this, plot that. So they kind of give you stepping stones to learn. It's not like you have to start from scratch.
So I have a temporary contract with doing data analysis for CMS that'll expire when I graduate high school. So how would you suggest in undergrad continuing to work with CERN?
Email professors who work on Atlas or CMS when you get to undergrad, and then present an Atlas or CMS group at your university. apply to REUs. These are like intern or funding agencies where you can work on research during the summer. Those accounts for you. They give you a mentor and stuff like that.
I don't know about what you will find, but I think being an undergraduate is a super busy time. Like, so I love the idea of doing it in the summer. If you can also work it in during the school year, I think an REU will also support research during the school year, right? Normally, I don't know. Oh, okay, no. So
Like two really big Atlas and CMS REU programs through Duke and University of Michigan. So a lot of students from all over the U.S. will apply to those two programs, and then they'll send you to CERN for the summer. And those are just for the summer. There's also like SULI and SIST internships to work at national labs, usually just during the summer, but I think you can like reapply and do that throughout the academic year. Yeah. Yeah. And then probably your university or the group that you're interested in working with will have resources to support the academic year. But also enjoy undergrad. Don't work too hard.
Yeah, the summer research programs are great. I mean, that's what I did. It's nice. Well, I mean, they pay you. That's one thing. You build your resume a bit, and also applying to them is kind of like applying to grad school. I mean, you have to like come up with like a little research proposal or statement of purpose thing. So it's good practice to apply. I think you had a question.
Can I become a physicist if I'm bad at math?
I think so.
Okay.
Yeah.
I was, well, okay, so I guess I've always liked math, but I was thinking about this earlier because it's like, okay, if you're good at math, like physics is great, but also I think there is a lot of math. You're not going to get away from it in physics, I'll say, but like with a lot, like hard work and perseverance, like, yeah, I know people in physics still who they're like, yeah, math is not my strong suit, and they're still here. You know, there's plenty of people. Most people, yeah, they love math, but I think if it's what you want to do, I'm sure, like, yeah, you can.
within physics, we have a whole bunch of different positions, or types of physicists. So maybe that means you don't want to go into like lattice QCD and theory, where it's all written like you mostly are working in analytic expressions. If you don't like that kind of stuff, but you do like getting things to work, then maybe you're more like a detector experimentalist, like a lot of us.
Yes.
Another fun thing that might be interesting is if you look up historical figures who were in physics, there are a number of them who were just admittedly very bad at math. So I'm thinking Faraday, for one, who has law and electromagnetism named after him. Bad at math. So like, you know, if you need to like, you know, and I didn't personally know him obviously, right? But like if you need to, you know, give yourself a little confidence boost, there you go.
I mean, usually when you're solving problem sets, usually you have to set up the problem right. That's half of it. Then you have to do algebra and calculus and stuff, all of it. So it can be a bit of a slog, but when you're in grad school, you'll find, at least in my experience, other grad students will help you. I mean, usually it's like a very collaborative environment, so it's like not like you're on your own. I mean, at the end of the day, like homework grades, there's like a very small amount. You have to take a test at the end of the day, but usually like, there's one guy in my cohort, I was talking about him earlier, but he, like, I would always like, Albert, like, how do you do this, Albert? And then once you learn, you do it enough times and you kind of figure it out. But I don't think it's definitely, especially, and now, like, I barely do any math. I mean, like, once you get past a certain point, once you finish grad school, or once I took my last exam, like, most of what I do is like electronic stuff. A lot of it's like project management. There's people that just like manage schedules and stuff. Like there's a lot of different ways you can be a physicist. It's not just pen and paper calculation all the time.
You're a theorist, you might just be
Yeah.
pen and paper
There
all
are
day.
people
So
that
if that's
do
what
that.
you like to do, you can still do that. It's just so many different things you can end up doing.
almost at time. Any final words? One more question.
Since there's like so many branches of physics, would you recommend sort of like investigating to try and figure out what you're most interested in physics?
So when you go to college, if you go to the physics department, there are usually seminars geared towards students. Like most departments have this, they'll have like a seminar series geared towards students in the evening, so it doesn't conflict with classes, where they'll have the faculty present on their research. That's where you can hear about condensed matter experiment, condensed matter theory, string theory, particle physics experiment, phenomenology, biophysics, all kinds of things. So they'll usually rotate through. You'll get to see over the course of a year most of the professors. I think that's probably the easiest thing.
This might not answer the question super directly, but I would also encourage you to think about what you want to be involved with a bit more broadly too. I think it's really good to, have a passion for a field, and you should follow that and, follow your curiosity. At the same time, be conscious of like other factors. Like, okay, is this person conducting the research somebody that I get along really well with? And would that, suit my style and how I approach things and my lifestyle? Like, do I, amount of time I want to be working on matches? Because even if you're working on something you love, maybe if it's not a great fit in like the research group, that can hinder your experience, and also vice versa. Maybe you're not like so interested in a certain topic, but you love the research group, and that kind of also fosters. So yeah, definitely explore like the physics itself, but just keep in mind some other factors that you're looking.
I'll just add that you can really switch around. Like the first physics you start, as we heard from some of the people, like people switch around subfields a lot, and so if you're not locked into when you start, and the skills are transferable. If you're interested in.
Yeah, don't be afraid to try new things. Don't be afraid to email professors. They might not respond to you. Just keep trying, and you'll find your way eventually. Yeah, we're out of time. I think your parents are probably out there waiting to pick you up, or maybe some of you drove yourselves. But that is the end of our session today. I'd like to thank the panelists for coming out. Let's give them a hand. We will be back next week with a talk on the standard model of particle physics in the LHC. So looking forward to seeing you again.